Hey everyone, welcome to another episode of Chips and Tips, where we're back today with the customer success team, and we're talking all about speeds and feeds. It should be a fun one, and Tim has been prepping for this one, so let's dive in and talk all the geeky details of cutting parameters with Tim. You want to start it off?
Yeah, thanks, Ben. So, I've been doing a bunch of homework about this, really trying to boil down 25 years of knowledge I've picked up down into whatever length this podcast is. Hopefully, we can keep it within a couple hours. This could easily be, a 40-hour podcast, and I'll spare everybody that. So, let's start off with, why are we doing this topic for this podcast? I think the real answer for me is that Paul asked for it. So can you speak to that a little bit, Paul?
Yeah, sure. Thanks, Tim. So as a customer success manager at Toolpath, I talk a lot of feeds and speeds with prospects, customers, and, folks in the machining industry. And, I've run machines a little bit, but my career has generally been on the software side. So it's always kind of been the game of, get the program together and hand it off to the guys and gals and say, what feeds and speeds do you run on this part, and kind of trust their judgment and what they know about their shop, right? And lately, I've been working with some tool pathers on getting their tool libraries set up, which getting your feeds and speeds right in those presets is a critical step there. And what I've noticed is I've seen a ton of different approaches. So as I try to navigate that, I thought it'd be helpful to talk to you, get an idea of, how you approach generating feeds and speeds, not in the sense that we want to define what everyone should run, because every shop's different, every machine is different. But really wanted to get an idea of what are the main variables you look at, and how do you approach the problem, and, what are some of the best practices you've found or seen over the years?
Yeah, great. So I want to talk real quick, kind of my priorities to cover in this. So I spent a very long yesterday trying to organize my thoughts. And the first one is to kind of clarify or, get on the same page with common terminology, kind of highlight the depth that will highlight the depth involved in sorting out cutting parameters, right? And then throughout there, and we'll make sure I'll ask the three of you to hold me to it at the end. Let's really make sure to kind of drill down into these are kind of how I think through adjusting cutting parameters, kind of how I think through sorting out new tool parameters, things like that. I'll share a real quick story. When I got into this industry right around 2000, so about 25 years ago, I right when I started programming, I remember asking old man Frank, which was my early mentor, hey, I've got this 1/4-inch end mill. What speeds and feeds should I run? And the machine I was running had like a 6,000 RPM spindle, and he goes over to his corkboard and he pulls off this little spreadsheet that he made, and it had an 1/8 inch tool, 1/4-inch tool, a 3/8 tool, a 1/2 inch tool, 3/4, so on. And then he had just IPM in the column right next to it, and it was like 27 inches per minute, 36, 45, 54, 63. And I remember asking him, where do those numbers come from? And he was like, oh, it's the chip load times the number of teeth times RPM. And I was like, yeah, where do those numbers come from? Right. And he was like, it's just what I found works, man. Run those, you'll be fine. And I remember my follow-up was like, was that for roughing or is that for finishing? And he's like, just run those. Just run those. And I was like, damn it. Like, I was literally having anxiety. Like, I don't understand it. And I think that's what I realized early, throughout my career, is like, I get anxiety if I don't understand it, and I get even more anxiety if I have to express it to people and don't understand it, right? Just because the reason I struggled in school, to be honest, was when I asked somebody why is this spelled this way, and they said, well, it's just because. I realized English was the dumbest language ever. So I started looking for patterns with this table that old man Frank gave me, right? I was like, it's got to be related to something. So I was looking at like chip load, I figured out the chip load. And then I was like, okay, I see a pattern there. Basically, every tool size he goes up, he adds a half thou of chip load. And I was like, oh, that doesn't make any sense to me. And then I was like, oh, wait, you can tie that back to the tool diameter. And then if I look down through it, it was like on the eighth inch, it was like 1.2% of the tool diameter. On the quarter inch, it was like under 1%. On the 3/8, it was like barely over 0.5%, and it kept going down. I was like, that doesn't make any sense. But they worked. So I'll leave it with that. Don't underestimate the value of shit just works. So before we get too deep beyond this, I do want to give a little disclaimer. This is a pretty hot topic for a lot of people, right? I'm sharing. Let's just be real clear that I'm sharing, my experience over the last 25 years. I've worked with a lot of different shops. I've worked with a lot of different materials. I've worked with several, actually quite a few, application engineers for different cutting tool companies. From a problem solving perspective, from like trying to set standards perspective. And then I also did it again when I was at Autodesk. So these are just kind of things that I've picked up. If you think I'm an idiot, be gentle, but feel free to tell me kind of how you handle your parameters. And from there, we can kind of dig in. Paul, you've been helping a ton of customers get their tools configured and set up for pre-tool. Have you noticed a pattern? And we'll talk a little bit about how we use pre-tool as a tool to kind of configure people's tools for our toolpath. But have you noticed a pattern of people like, oh, this is how I want to set up my tools? Or can you speak to that a little bit before we move on?
Yeah. So, before even getting into like a pattern of the actual cutting parameters, the first thing I see is kind of what people are running and kind of the speeds and feeds that they think of when I say like, what are your cutting parameters to this tool? And, I would say it varies greatly with what I get. You mentioned chip load there. That's kind of what we use with pre-tool on the back end is that, chip load is a percentage of tool diameter. So almost everything I do, no matter what somebody gives me, is trying to get to that. But I would say most consistently, I get, maybe SFM, maybe not, a lot of aluminum. And I know that there are some variables there we might talk about. Probably most commonly, I get this is the RPM and this is the feed rate or inch per minute that I want to run at.
Okay. That sounds like they went to the school of old man Frank. So that I try to say that it sounds like I'm saying that as a put down, right? But there is something pretty valuable about like it just works, and this is how I've been doing things for a long time. It works. I make money. I make profit. All that kind of stuff. So there's a ton of variables. I'll kind of weave in some anecdotal stories here and there. I think one of the first stories that I'll share is I used to build real high end 2-stroke shifter cart engines. I was really good at it, and I was trying to break that down into a system, kind of a systemized way of building a new engine. And I remember I came up with like 14 different things, ignition timing, cylinder head, port timing, all those things. And then I was trying to come up with a systematic way of like coming to the best result. And I remember like, crap. So if each of these 14 variables had two options, how many total variations would I have to test? Right. So my thinking was if I change a cylinder head, I have to change different pipes to see how, that change was affected by the pipe. And then I have to change the carburetor tuning, and then I have to change the ignition timing, all these things. And I went down the path of like, how many variables is that? And this does turn back to everything relates to racing in my world, but this does relate back to what we're doing here. So the formula for that is, you have 2 options per 14 variables. That's 2 to the power of 14. Let's play the guess it game. What is the number on that? If you have two options for 14 different things, anybody want to take a guess how many variations you might have? Let's make it quick. There's no reward or punishment if you get it wrong.
I don't know.
Say it again.
A whole lot of them in the millions. I don't know.
16,000. Good job not committing, Scott.
Yeah. Well, I didn't understand the question because I was like, surely it's more than 28, but
yeah. What it is it's how many options you have. So in this, it now relate it back to cutting tools, right? If there was 14 different variables, which is what I did last night, is I counted up like how many different things do you have to consider that affect a cutting condition. Very easily 14 things. We can go through them here in a second. But if you only had 2 options for those, let's say coated, not coated, let's say tool diameter, rake relief angle, all that kind of stuff. If you only had 2 options per variable, it's 2 to the power of 14. That's over 16,000, variations, right? So when I was looking at this engine thing, I was like, well, surely I can't, test 16,000 different things. I'm going to have to boil that down to something smaller than that. So I was like, okay, if I had 4 things and each thing really had probably like 6 different variations, which is also relatable to cutting parameters. Well, that ends up being 4,000 different variations, right? I'm like, I don't have enough time to do that. So really what I did is I used kind of my deductive reasoning to come down to like, all right, well, really, I'm going to break it down to, let's say, a few different things with a few different options. I came down to like 80 different things I had to actually go test, right? So I share that story because I feel like it does relate to our cutting parameters, right? There's what seems like this, abstract amount of variations and variables, right? And we're going to get into like nomenclature of cutting tools and cutting parameters and stuff like that. Yeah. So we're all on the same page. But what?
Yeah, I was just going to say, really, there you're only talking about it's like that just with homogeneous materials, like steels and aluminiums, right? But I spent 10 years trying to figure out how to program timber. And
that's crazy people stuff, Scott.
Batch to batch for sheets of plywood would vary. And there were some exotic plywoods we used to use, and then all the different grades of timbers for soft and hardwoods and exotics. And some timbers harder than Carl Bass will tell you. Some of the timbers are harder than steel by significant margins, and you just burn up carbide like that. So that was definitely a dark art. But so I struggle enough trying to figure out feeds and speeds for aluminium, and steels. So totally.
I ran into that same thing a couple of years back. I had the Pocket NC when I was on the Autodesk support team, and we did a project where we were looking at I was training the support team about the motion of some of the different 3D surfacing tool paths, and really showed my gap in knowledge there with feeds and speeds, because I think this is a black walnut that sat in somebody's garage for years. So, that started with a Google search for me, which was pretty much fruitless. I was looking for surface feet per minute, maybe a chip load if I can find it, found 10 websites that directly contradicted each other, and then just put it in on aluminum feeds and speeds and ran with it because time didn't matter in that situation. So
my takeaway from that, I always think of these stories is like, what is the goodness in that? And how can I apply that to something else? Right. So that's what I'll say. This seems overwhelming, this topic, and we'll get into the overwhelming part of it. But sometimes you just have to make a decision and move forward. Use some deductive reasoning, make a decision, move forward. When things go right, try to understand it. When things go wrong, try to understand it. Right. So to talk about those to the power of numbers again. So, I ended up boiling that engine, program down to like 3 main variables, and there's four options for each of those variables. Right. That brought it down to only 80, 81. It's 3 to the power of 4. It's like only 81. Well, that I can actually chunk through that in a very mindful testing kind of way with the spreadsheet. So, let's move on. And I want to start with, I was trying to think of how to tell this story, right? We're trying to entertain people, keep people's attention. And I was like, man, if we thought of this whole podcast like a joke, can I keep people's attention long enough to get to the punchline? And I decided, actually, let's just get to the punchline and then hope that keeps people's attention long enough. So, I'll go straight to my punchline of a realization I had that Justin actually mentioned on my Slack. I mean, on my Instagram last night. So Justin Gray, our CTO, he and I have had these cutting parameter conversations to nauseam. And one of the things he said was, one of the big realizations he had was that chip load across the family of tools, let's just like MA Ford 138 series, right? That's a standard for many people for an aluminum rougher and finisher tool. If you have a 3x diameter MA Ford 138 and you dial in cutting parameters for an 1/8 inch tool, once you figure that out and where it's cutting good, healthy chips, it's lasting a long time, leaving a good finish, you'll realize that your cutting parameters, your main cutting parameters, that's going to be, if you're cutting at full flute length already, it's a 3 times diameter tool, right? Your step over and chip load will be a constant as a ratio to the tool diameter. Let's just say like 2%. The chip load is going to be, let's say, 2% of the tool diameter. If you figure that out for an 1/8 inch tool, it will be the same. And I say this with strong conviction. It will be the same for a 3/4 inch tool, or 1 inch tool, or 1/2 inch tool, 3/8 tool, so on and so on. Until, and this is the super, super important part, and it's something that actually took me longer than it should have to realize, but that is a flat, ratio of percentage to the tool diameter until you find what I call a limit. And understanding those limits, that's kind of the black art. Some people say, black art or black magic, or, some magical thing. And really, it's magical because there's so many freaking variables. But let me make sure I am staying on my talking points. Yeah, so we're going to get into understanding the concept of limits here in a second. I realized this kind of general thinking, honestly, it was probably 20 years ago. I was going off of old man Frank's kind of feeds and speeds and speeds and feeds, or whatever the terminology is. We'll talk about that in a second. But and then I got handed a Inconel job that was way too early in my career. And that was back before there was really good cutting parameters that was shared freely. And so I completely stumbled on some parameters that were working for this 1/4 inch tool in this Inconel part. Anybody who's cut Inconel, it's like watching snails have sex. It's like you can't really tell if anything's happening. But it's incredibly boring. And then I was trying to find good parameter for the next size tool up for another feature, and I was just killing tools, just murdering tools. And then that's when it hit me. It was like, wait, if I figure out the ratios, the chip load ratio to diameter, if I figure out the step over as a ratio to the diameter, Maybe let's try that on this 1/2-inch tool or 1/4-inch tool, whatever it was. And it just worked like freaking magic. So we'll get into the kind of the terminology, so we're all on the same page here in a minute. But that was kind of my realization. Was like, oh, I think I'm on to something. I'm far, far, far from a genius, but I do pick up patterns pretty well. I do understand kind of mechanical things pretty well. So let's move on to understanding the concept of limits when it comes to cutting parameters, right? I break limits into a couple different categories. My buddy CJ actually added the second category, when I was thinking through this problem. And the first category I call mechanical limits. A lot of people feel like a limit that happens, like I go out to the machine, I get chatter. It feels like somebody's torturing a cat, right? That's really not, chatter isn't a limit. Chatter is a byproduct of several other things that we'll be talking about, coming up. But really what you're talking about with a limit, a lot of people talk about horsepower. There's a pretty deep conversation on our team last week about horsepower. Maybe horsepower is the magical number, and horsepower is just one of those inputs of these 14 different variables, right? So if we talk about horsepower, we have to talk about torque. These are things like, I'll encourage people, if you're listening to this, if you're not driving, grab a notepad, talk about write down some things that you should learn more about. Horsepower and torque, and horsepower at different RPMs, right? So a machine can have 30 horsepower, claim to have 30 horsepower, and it might be for a sliver of the RPM range. But then the torque is like grossly somewhere else in that RPM range, and it's only, it's usually a little broader, but it's somewhere else. Some machines advertise 30 horsepower, and they just don't have it. Stall the spindle if you get a true 30 horsepower cut. So moving on from horsepower and torque, those are super important. Go learn about them. The internet is full of great information about them. Any machine really should have some data in the manuals that it comes with. Some of the higher end machines will actually give you torque curves and horsepower curves and all that. And like some machines, you're not really supposed to run a full horsepower draw on the machine for full duty cycle, meaning 100% of its life. They'll actually give you.
I should just add there, Tim, that like I think if you're going to go look that stuff up on the internet, some people may realize this, but power torque curves are quite different from combustion engines to electric spindle motors. So just make sure you're looking it up for electrical motors.
Yeah. To call that out very specifically, I would be searching. I'd be looking to learn more about the horsepower and torque curves and how they relate to your machine, and how they relate to machining and cutting and things like that. So going down my list of concepts of limits, right? So we talked about horsepower and torque. You have machine motion dynamics, right? So if you want to feed at 800 inches a minute, your machine, there's a motion dynamics where my VF2SS in my garage, if I want to feed 800 inches a minute across 3 inches, it's just not going to happen because the machine has to accelerate and deaccelerate. And then also even has to make turns. Some machines, it's like driving a school bus on a racetrack. Other machines, it's like driving a little go-kart on a racetrack. They turn real quick and nimble, accelerate fast and slow down fast. Other machines accelerate slow and slow down slow and have to slow down to make accurate turns, right? Tool holder rigidity. Now, let's just say tool holder limits, right? So that's going to be rigidity and grip force. How tenacious are they going to hold on to the tool? How rigid? I think everybody on this call except me have some engineering background, could explain, beam bend formulas and all that stuff better than me, but I don't think we have to go down that path. Beyond your tool holder, you have spindle taper. We'll just call it spindle taper. And to me, that's condition. That's the design of the spindle taper. That's the rigidity of that interface, right? The condition of your holder and the taper and how it all comes together. Is it just a Cat 40? Is it a dual contact? There's so many things that could be a limiting factor when it comes to your spindle taper. In that same kind of topic, you have your pull stud and really your pull stud and drawbar force, right? We're going to talk later about tool helix angles and how that impacts side force on a tool versus pull out force, and how your helix angle of your tool impact those two things. You can get chatter. Chatter is like basically the thing we're all trying to avoid. That is like the most recognizable cutting condition problem that people have. And I would say the number one thing people are trying to avoid. You could be getting chatter from too much side force on your tool. And then you could also be getting chatter for too much, pull out force on your tool. So we can talk about that more later. And then overall rigidity, that's like the rigidity of what I would call like the system, right? That's going to be the system to me. Anything involved with cutting, that's the work holding, that's the part, that's the tool. Your cutting tool is actually probably the most rigid thing in the whole system. Carbide, the what is it? The elasticity of carbide is like, significantly lower than everything else in your whole system assembly, right? But the system to me goes from, basically the table up through the whole entire assembly and machine, right? Paul mentioned, what was the machine you were playing with the walnut part on, Paul? Remind me the name of that. I'm drawing a blank.
It was an older Pocket NC.
Yeah.
So maybe the V2 with like the, I think, 10K spindle on it.
Yeah. So an older Pocket NC is quite a bit different than the newer one, right? When it comes to just your whole system rigidity.
If you think about like the percentage of material in the machine as well, at that context, like that carbide tool represents a way higher percentage of the overall machine than a VMC, right?
Yeah, exactly. That's a really good point, Scott. Yeah, I think those tools will they hold up to either an 1/8 inch or a 1/4 inch shank tool? Can you remind me on that one, Paul?
I think mine went up to a 1/4 inch, but I only had 1/8 inch tools. So that was the other variable, is everything I was running on that little machine was, probably length out of holder. I mean, probably at least 10 times length to diameter ratio, everything in that machine. So
you're getting to a really important topic we'll be talking about in a minute, is that everything is length to diameter is basically how I think through things. But man, Scott just broke my brain. I've been doing this for 25 years, and the percentage of carbide in relationship to the system assembly, right? That's a really interesting thing to think about. If you had a 1/4 inch tool sticking out 1 inch on your Pocket NC, and then you start thinking about the density of that and the relationship of the whole system, it's a huge percentage of the whole system mass, right? Versus my VF2SS, which is, it's a tiny percentage of the 8,500 pounds, whatever that thing weighs. But my point with the Pocket NC is, like, I've seen the early ones versus the newest ones. There's a gross difference in your system stability and rigidity there. And now you go from there, let's say from there to a Datron, or let's say from there to a, one of the smaller Tormacs. There's another big jump in system mass, rigidity, all that stuff. Then you go to a Datron, then you go to a Haas, and you kind of go up the line. The whole system really, really matters. Talking to kind of finish up the hardware limits, to me, to finish that thought, you're going to have work holding reliability and rigidity, part feature stability and rigidity. There's some wall width to length height ratios. There's this golden 8-to-1 ratio that people talk about. You can make anything you want, really. It's just how much work do you want to put into it. But your part has a big factor in the whole system.
Okay, then you
So
get
from
pins and
there,
stuff as well.
yeah, like that's
Yeah.
what we're talking about, right? If you have a 1 millimeter thick wall,
Mm.
whatever an is, you can comfortably machine probably about an 8 millimeter tall wall without any real hassles. Once you get above that, you have to start doing like what we'd call like a waterfall technique to, go back and forth from side to side and do all kinds of really crazy, techniques to machine that wall well. So moving on from what I call machine limits to human limits. This is humans screw everything up, right? This is what I call the CJ factor. Shout out to CJ, my friend CJ Abraham. We were having a blood battle about this whole topic about, being able to scale cutting parameters over a series of tools and how it should be done. CJ wants to solve all of the world's problems through some code. And really what we realized is there's a breakover point. I said, you could apply this chip load or radial depth of cut as a percentage of the tool diameter in a linear path, right? 2% all the way across until you hit a limit, right? And so we were debating, well, is this where the limit should be on a Haas VF2 or is this where it should be? And I was like, dude, I can tell you this half-inch tool, when I go from a half-inch to 5/8, it's like a huge difference. And I can show you some numbers later. But and CJ's like, I don't want to see my machine running that fast and with your stupid half-inch tool. And he's like, I'll run those numbers up to, let's say, a 3/8. And we started having a debate about what the limit should be, and I realized, oh, there's a human limit, and that's comfort zone. I mean, it could be as simple as like, I just don't like my shop being that noisy. So whatever, pucker factor is kind of what I call it. Noise, stress. Some people have a concept of the machine being in stress when it's cutting, at certain level of aggressiveness. I have a graph. If we want to try to do a screen share, it's probably a good time to try that. What do you think, Ben?
On that point about machine stress, sometimes it seems like the machine is being stressed out and there's lots of noise being made, but it's really just the sheet metal or the plastics on the outside of the machine that are oscillating, and so often you end up with like big flat plastic surface areas and it's like a bellow just like pumping backwards and forwards.
Yeah.
But the machine structure itself and the tool cutting condition is perfectly happy.
Yeah, that's a good point. I think you just you were just Saudi Arabia experiencing that on a machine, weren't you?
Mm-hmm.
Yeah.
You pulled that up. I've got a fun little story making parts on the Brother versus the Sile. They're two different machines, but both BT30. And it's interesting to see how they behave even with the same tooling. You can actually see firsthand, like, oh, okay, this is way more torquey. It's got a higher horsepower rating, but you can tell you can push it way harder than the Sile. We accepted a job on Xometry many months ago. It was like when I first started, and we were doing Xometry work as an R&D thing for Toolpath, and decided to order a 10 times diameter 3/8 tool. And we chucked that thing up in. Now we actually had Rego Fix too, but we chucked it up in like an ER16 BT30. I mean, the thing was like this big. After we stuck it up in there. And we used the cutting parameters. I believe it was Harvey or helical or however you say it. And we're like, yeah, helical. And we're like, oh yeah, we'll just put in the feeds and speeds for this. And oh my gosh, it was the loudest, most unsettling thing you've ever heard. And we actually ended up snapping it. And that's when it was in a Rego Fix. So we were trying to eliminate, okay, is it tool deflection? What is it? And I reached out to Ethan Patain, which you guys might know him from Instagram and stuff. And he's like, no, these are the parameters I use. Turns out he was running on a Cat 40. We were running on a BT30, and it's just two completely different things. So it really is it's a tricky thing to narrow down, so many different parameters and rigidity. And Yeah.
It's tricky. I have a horsepower calculator that I want to show later to talk about exactly what you were just talking about. Is not all if you're limiting by horsepower, trying to find a pattern related to horsepower, I'll poke holes in that here with a spreadsheet I have later.
And I've
I'm
never got used to seeing a BT30 either. Every time I see one, it always surprises me how small it is. You know,
It makes it-
and it's actually the same because you with the Cat 50 or BT50, you don't see those as often either typically. And when you compare when you compare it to a BT40, it's like the same shift. Yeah.
So yeah, so this is our friends at Command. I was holding up a Cat 50. Anybody watching, I'll try to verbally express it. So every time I hold up, yeah. So as a banana comparison, my head is bigger than a banana. This is a Cat 60. I was on Instagram and I posted a picture of my hand holding a Cat 50, and I made a comment like, "Man, every time I see one of these things, I'm just surprised how big they are." Cat 40 is probably the most common. Cat 30, every time I pick one up, I think the next day I picked up a Cat 30 and was like, every time I see one of these, I'm surprised how small they are. Command sent me Cat 60. Just I use it as a bookend. But this thing is huge. I have an extra large size head, and it is about Tim head size.
I was trying to take a screenshot of it.
Okay.
I wondered what was going on there. I was like,
Yeah, I was wondering. So I have an extra large size head. Share screen cap.
We'll figure it out later. Don't worry.
Anyways, that sucker is monster. And I've had the pleasure. Let's get rid of that. So I've had the pleasure of cutting with a few Cat 60s. Not surprisingly, you're not spending them at 20,000 RPM, but they're very, very rigid, and it's a mind bending. You know, the difference between a Cat 30, Cat 40, Cat 50, Cat 60. Then you get into HSK spindles. It's a totally different dynamic. If people want to spend some time just learning about the different spindle interfaces, I mean, use your example, Ben. So the style has a BT30. The brother has a BT30 at our toolpath shop. I assume the style is not a dual contact, is it?
It's not dual contact.
Yeah. So if you start testing that, anybody that wants to learn more about that, go spend some time Googling that, and why dual contact is basically touching at the flange and the taper at the same time. Requires a lot more precision during the manufacturing of all the tools, the spindle and all that. But it's a grossly better interface. So I was trying to share this graph, and I want to share it. So let's work through.
while you're sharing that, I just thought I'd just in Unit Wars, just point out.
Let me cut you off real quick. Can you see Can you see this while you do that?
Yeah.
Okay, perfect. Keep going.
BT40 is more common than Cat 40. Just saying, just there's.
Thanks for that clarification. All right, so here's a graph that I worked on. So here's my PowerPoint presentation. Everything there is to know about cutting tools and cutting parameters. That is not what we're going over today. But so where's the limit? If you look at the graph on the left side, this is a chip load as a percentage of the end mill diameter. On the y-axis, anybody that's looking on the y-axis or listening, anybody that's listening on the y-axis, we just have a percentage of the tool diameter. And in this graph on the left, it's at 2%. So on the x-axis on the bottom, tool diameter starts at 0, goes in increments of 1/16 of an inch, all the way up to just over 1 inch. So in the ideal world, where the machine's not a factor and all the other mechanical limits are not a factor, that's how we would set up our tools. In most tool catalogs, most modern tool catalogs, when they're giving you a cutting parameter, that's typically how they scale it from small to big. Some people might use I don't know, whatever the brand name is. They go to use this 3/4 inch tool, and they're like, "Oh, these tools are garbage." I just used their cutting parameters out of the book, and it was garbage. More than likely, those are good numbers. if it's a reputable tool company, it's probably good numbers, and you're just finding a limit that you haven't figured out yet. So where's the limit though? So let's look at what it says on the bottom. So we have constant parameters on the lower left. So let's just say we have a 12,000 RPM. A chip load is a 2% ratio of the tool diameter. Axial depth of cut, we're going full flute length. These are 3x diameter tools. That's considered a fairly standard, tool, not stub flute, not long. If anybody's taking notes, like I consider anything 3 times diameter and smaller, like just really solid. Once you get up to about 4 times diameter, you have to start thinking about changing some cutting parameters to get that to cut well. You can do that pretty easily up to 5, maybe even 6 times diameter, where you can make some pretty easy adjustments. Once you get up, in my opinion, once you get over about 5 or 6, you have to start looking at like short flute, reduced shank type tools. But then, yeah, go.
That's a good call out, just for, maybe some of the listeners that I've worked with in pre-tool to get presets set up. What that does is applies some of the scaling factors I think Tim's going to talk about down the road here.
Yeah.
From L to D ratio of 3XD to 5XD. And, what Tim and I have spent a lot of time talking about is like, maybe we could get 6 in there, but really anything over that is like tools that you want to be looking at closely. And, hopefully you're not running too many of those. That's a huge amount of the tool library update time.
Yeah, pre-tool has a lot of room to grow, right? It's a really valuable tool now, and we're having internal, planning sessions for where it goes in the future. But so looking at these, these numbers, where would the limit be? And I'm just going to share on my VF2SS that's got 1 million miles on it, but still has good spindle condition, good drawbar force. The horsepower requirement is on the right. So the only variable here is the tool diameter. So for a 1/4-inch tool, it's only 3 horsepower draw to make that cut. A 3/8 tool jumps up just over 10 horsepower. A 1/2-inch tool is just over 24 horsepower. And my 30 horsepower machine, it can take that cut right there very comfortably. People talk about Haas not reporting their horsepower numbers, right or whatever. I'm telling you that 24 horsepower cut will cut just fine on my machine. Now, the big difference is if you think about the difference from a 1/2-inch tool to a 5/8 tool, and for any of our millimeter friends, just to break it into fractions, that's a 0.5, size tool, or 500 thousandths tool to a 625 thousandths tool. So it's not a huge jump, but following 3 times diameter, 30% of the tool load, 2% chip, 2% of the tool diameter for chip load, that horsepower requirement for that tool goes from 24 horsepower to 47.
It's just occurred to me. It's like horsepower to drag ratios for aerodynamics in racing cars. It's the same. It's just expensive.
Everything relates back to racing, Scott. Yeah. Yeah, exactly. It's this really interesting jump, right?
Yeah.
But it does. One of the things you'll see there is that, if you follow this linear line, the horsepower requirement takes these jumps that might surprise you. So what do you do about that, I think, is the next question, right? So if I go to the next slide, we could have a very slide heavy, presentation about this, but I try to keep it pretty minimal. So looking at 2 things we could change here, right? A lot of people just start throwing stuff at the wall to see if something sticks. But let's use the 2 variables and then understand how it changes the horsepower requirement. And then I also want to talk about chip thickness. We'll talk about that in a second too. But many people's instinct. So what would actually happen on the machine? So let's go back to that, where I put that red arrow. What would happen on the machine? So let me tell you, in my opinion, one of the I don't make a habit of crashing machines or breaking tools. I imagine that it's got to feel terrible. But one of the worst feelings I've ever had is stalling a spindle. It is not a fun experience. But that's what would happen on this. If I went out and ran that on my machine, it would probably put up a short fight. Hopefully I would catch the speed hold or e-stop before it really stalled. But
So
that
just
would stall
just
my
a
machine.
question for
What's
my.
that?
So is that red out back on that other graph? If you just go
Yeah.
back a second. So
Yeah.
on the right hand graph, you've got the it's just going up linearly at an angle. That is that red arrow on that graph where the machine stalls. Is that what you're saying?
Yeah. So this is me identifying where I'm going to have a problem, and that's me doing it out at the machine, experiencing it at the machine. Also, doing some calculations and just knowing like I'm going to have a problem here. In
Mm,
this case, the tool's short enough. I've got really nice short holders. Rigidity is not really an issue for me here. For anybody listening and not watching, on the left, we have a graph that's just a horizontal line because our y-axis is a percentage of the tool diameter. Our x-axis is the tool diameter. On the right graph, the y-axis is chip load as a calculation, as a measurement. That's 2% of the tool diameter. And on the x-axis is the tool diameter. So the arc of the line basically is just a linear line that goes from the bottom left to the top right. And I have an arrow right at the 5/8 diameter tool at the intersection of the chip load and the tool diameter. And that, if you read the text below it, that's showing the point that there would be a 47 horsepower draw to make that cut. And on my 30 horsepower machine, that's probably getting a little less than 30 horsepower.
right.
That would absolutely stall my machine. If you go
Cool.
back, a couple points to the half-inch tool, that's only a 24 horsepower cut, and that would be no problem. So that's me kind of identifying my A limit. In this case, it's really just a horsepower limit. The limits get more nuanced and harder beyond that. But did that answer the question, Scott?
Yeah, that was great. Perfect. Thank you.
The horsepower limit for your machine, the VF2, and it sounds like when Al was at track last week, he ran into it at the 3/8 inch tool
Yeah,
diameter.
yeah, exactly. And go, Paul, go.
Oh, yeah. So, just an example we all ran into last week on kind of finding that limit, right?
Yeah. So on the machine Al was running last week, it was 3 horsepower. I believe it was right around 3 horsepower. So that's grossly different, right? And then, he was running parameters out of pre-tool. So we haven't really talked about what those parameters are or how we handle this in pre-tool. And I think he was running a fairly long cut. So there's a lot of variables that we haven't really covered, but he found a limit, and so moving down from there. What do you do at that limit, right? A lot of people's instinct is to cut the chip load until you get something that works in your horsepower range, and that's a viable option. It's actually probably about my second option that I would pick. But then for me, my kind of first option is, and we're talking about an adaptive style, constant engagement, roughing toolpath here. My instinct would be to reduce my, Scott, help me out. I'm drawing a blank on what the step over in adaptive is called.
I mean, oh man,
We're both fired.
hang on.
Uh,
I've got it here.
okay. So essentially, your step over and adaptive. It's not a true step
Optimal load.
over. Optimal load. Thank you. We're going to talk about tool engagement angle here in a little bit, but I wanted to kind of cover the punchline before we get into the boring, nomenclature of tools and tool paths and all that stuff. So this is my instinct is to reduce your optimal load, or essentially your step over. So in this example, in the yellow at the bottom, for people watching, the graph is similar to last time, but when it changes from a half-inch to a 5/8 tool, the line drops drastically from 2% to 1%. when we're talking about chip load. And so to give you some numbers on that, if all we did was cut the chip load in half, we go from, what was it, a 47 horsepower cut to a 23 horsepower cut, almost 24. So we have a drastic drop in, well, it's half a drop in horsepower, right? But the interesting thing here to just kind of note in the back of your mind is the chip thickness there would be about half the thickness, the median thickness of the chip, because chips have a thick side and a thin side. We can dig into that another time. But let's look at what would happen if we took the radial depth of cut and cut that in half. So we go from a 30% step over or constant engagement or optimal load, whatever we're going to call it, to a 15% optimal load. And this is 15% of the tool diameter. Then we would drop to the exact same horsepower requirement to make the cut, 23.73. But the interesting thing here, and I don't know if we're not going to make a assertion of what this means yet. But the interesting thing here is when you reduce the optimal load or the step over constant engagement, the chip thickness would be 70%. The average chip thickness would be 70% of what it would be at a 30% step over. So what that means to me, I'll make a quick assertion. What that means to me is you're maintaining a thicker chip. Thicker chips, it's really important when you get to harder materials. Thicker chips, the chip is the main source for pulling heat out of the cut. A very thin chip doesn't pull a lot of heat out of a cut, and a thick chip pulls more heat out of the cut. So what that means with aluminum is you'd have less galling because the chips are pulling heat out of the cut, meaning out of the material and out of the tool. In harder materials, let's say work hardening materials that have high nickel content, you would have less work hardening. And in just harder materials, you have less heat in the tool. And heat for harder materials, that's where you kill tools. So let me see if I can figure out how to stop sharing. Hopefully, man, this is a deeply technical topic, right? I was gonna have a beer to help get through this, but it's too early in the morning for me. Does that make sense? Any questions about that before we move on?
I'd love for you to go back and explain those second two graphs in the same way as you did the one with the red arrow, if you could. For sure. And just for some, like when you start talking about chip thickness and chip load, they sound so similar to each other, but they're actually quite different, right? So,
I have a visual for that. I have a visual for that, and don't let me get away with not showing that when we start talking about probably chip thinning. I want to make sure to pull up the visual for that when we talk about chip thinning. Let me handle what you were talking about with. Can you guys see the graphs again?
Yeah, Mr. Back. Yeah.
Okay. So the graph on the left, it has the y-axis is a percentage of the tool diameter, and it's at 2%, starting at the small, and it goes up to half inch. So the x-axis is your tool diameter. So it stays a constant flat trajectory at 2%, and then it has a drastic drop when you move to a 5/8 diameter tool. And that drop just shows that we're now have a chip load of 1% of the tool diameter. And our aim here is we've found a limit. And in this case, the most simple limit to identify is the horsepower requirement, right? And then if I'm being super honest, this graph was made at probably midnight last night. I just made it a straight line from 1% down to about 0.5% between 5/8 tool and 1-inch tool. I'd have to go sanity check that, but that's basically how I've had success. Is like once you hit a limit, it ends up being a falling factor because your horsepower keeps going up and up and up, and you're flirting with the edge of your power, right? And then the graph on the right is just a representation of that, where the y-axis is your chip load, so in inches. 2% of the diameter of the tool from 1/16 of an inch up to 1/2 inch, and then it drops drastically, and then it slowly drops after that.
Why does it have a bit of a bow in it after?
Yeah. That's let's ignore that for now, Scott. That's a midnight visual. I was like, damn it, I don't have time for this. Yeah, that's a midnight visual. That's my cop out for that.
Fair enough.
Any other comments or questions about that before we move on to my next topic to cover? Is going to be cutting parameters, kind of the essential terms that we need to talk about. Nope.
No,
Okay.
my only thing is more silly than anything. I think we should call this, instead of a TED Talk, like a Tim Talk, because you're just dropping all sorts of stuff on us, and it's great. It is highly technical. This is great. I'm enjoying it.
It's a deep topic. I honestly was just being very open with friends. I stressed about this a lot because there's only 16,000 things to talk about, right? Okay, now I think it's important for all of us to get on the same page when it comes to cutting parameters and talking about basically the naming of these parameters, right? I'll kind of talk about them a little bit. This could really be a 40-hour talk, right? Or a whole college semester. And it would still not be covering everything in depth. So when we talk about cutting parameters, I'm gonna go over the essential terms, right? So this is speeds and feeds. This is just a funny topic of, is it feeds or speeds, or speeds and feeds, and how is it? This is the way old timers think of it. My buddy Angelo, shout out to him. He's a stickler on this. Old Man Frank. Anybody that hears me talk about Old Man Frank, there's actually like 3 old mentors of mine that I cluster into one person for storytelling purposes. But actually, Lock 2 was my one of my first mentors, and whenever I would say feeds and speeds because it rolled off my tongue better, he's like, no, it's speeds and feeds. Speeds come first. You have to figure out your speeds before you figure out your feeds, right? So just for clarification, what is speed? So speed is basically your RPM, and what it actually is it's the speed at which your cutting edge is passing the surface of the material. One way to think about this is if you took a 1-inch tool and rolled it across your table or your desk, how far would it travel if flute number 1 started and then rolled 360 degrees and got to flute number 1 again? It's essentially the circumference of your cutting tool, right? So for every 1 RPM you travel on a 1-inch tool, it's 3.14, right? It's pi times diameter. Yeah. That should be simple math for many machinists. So how many of those do you go per minute, right? So it's surface speed in most of America is measured in SFM, so surface feet per minute. But the real thing that we care about is, what does it actually mean to the cut? So it's the primary factor for heat generation. Surface speed is your primary factor for heat generation. Maybe not all of us, but I sure the heck, when I was a kid, tried to make a fire with a bow and a stick, right? And the faster I could spin those two surfaces together, the more heat it generated, right? If you haven't tried to start a fire with a bow and a stick, it's a lot of work. But that's your primary factor for heat. So the higher your surface speed, the more heat you generate. And we actually want heat in some of our cuts, or I would say all of them, right? Without speed, you don't have chatter. That's another important factor. If your RPM is 0, you will not have chatter. So there's some resonant frequency to talk about. A lot of people have opinion of with speed comes chatter. It's not really accurate, even though when I have chatter, we'll talk about kind of my rules. My first thing I do is I reduce my speed. That's kind of a very first thing to do. To be honest, I reduce speed and feed together as a percentage, so my chip load stays the same. So I'm only really changing the surface speed. Resonant frequency, something to write down and learn more about. My kind of fun story with that is, like, I think the way my brain thinks is every assembly has a resonant frequency. I'm not a physics teacher, but I'm going to give you my machinist, motorcycle racer, rider kind of perspective of this. Every assembly has a resonant frequency, and that's basically a frequency that it wants to just start kind of wildly, vibrating, and the vibrations feed itself, and it makes it worse and worse, right? On many of us has been in an old crappy car, right, going down the freeway, or on their bicycle, or on my dirt bike, right around 90 miles an hour on the dirt. If the terrain is just perfectly bumpy enough, it gets what we'd call like speed wobbles, right? And when I get to those speed wobbles, I have two decisions to make. The rational decision. Yeah, exactly. The rational decision, which, somebody with a good sense of self-preservation would slow down, and they would get out of that resonant frequency, right? If you want to win the race, the other option is to hurry up and go faster and see if you can get through that resonant frequency quickly. If you muddle around in it, usually it's not the good place to be. My dirt bike, for whatever reason, with the way it's set up and the tires and all that, if I'm on a fire road doing about 90, it gets kind of sketchy. But I can actually, accelerate through it, and it gets real sketchy and then calms down. Translating that to cutting, let's talk about a lathe, right? So in a lathe, we'll say a Haas lathe. Mark Terraberry, we just had a podcast with Mark Terraberry. They'll show after this or before this. We'll decide later. But he had a really good point on lathes. If you get chatter, most people's instinct is like manually overrides feed and speed down, 10% at a time until the chatter goes away. And that works really good. It's worked for generations, right? On some machines, just lighter machines that don't have a ton of mass, one option is to boop, 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 increase them. So the chip load stays the same, but the surface speed goes up. On like your smaller ST10 type Haas lathes, that actually is a good way to make your chatter go away. We'll talk about tool coatings and stuff like that, and carbide substrates and heat and all that later. That would actually increase your heat. So that becomes a separate problem. So then you need to start looking for ways to kind of mitigate that. But that's a little bit of a little deeper dive into surface speed. But
and also an interesting thing with the Haas lathes, not all lathes have it, is they've got the spindle speed variation code, so they can oscillate the actual speed of the spindle, which will just kill the harmonics as well, which is really nice. It's a shame that's not available or not practical to be used as much on mills as well,
Yeah, 100%. Yeah. So there is I believe there's a good tip of the day, or one of the Haas videos. I don't know if it's specifically a tip of the day. It might have been John Nelson or someone doing it. But,
true. Yeah.
Go to YouTube. I did learn recently the Haas tip of the day is just Mark Terraberry. So it might be one of the technical videos. So go learn more about that. So a less talked about topic when it comes to surface speed is it does impact the shear, and the shear is how you basically create a chip. The higher your surface speed, the lower your shear could be on many materials. Which would reduce. It's a more complex kind of thinking. But,
say that again.
The higher your surface speed on some or many materials, a lot of times like steels and stuff like that, your shear, the shear force, it lowers. And And there's you guys are all smarter than me. You can go learn more about it. PH Horn does a really good talk about this. I hope it's on YouTube somewhere. I went to one of their I don't know where I stumbled into one of their workshops, and that was the first time I was like, oh, that made sense of some things that I experienced throughout my life. So all right, so moving down the cutting parameters, we have feed. We'll keep that pretty short. This is just your chip load. It's specifically your feed is your chip load times your flute count times your RPM. That equals your feed, right? Your feed is your primary function for force, right? How much force is being put on the cutting edge of your tool. We mentioned chip load there for a second ago. So chip load, what is chip load? It's just your how much your tool advances per flute per revolution. So essentially, how big of a bite is each flute taking out of the cut? So you'll hear like 2 thou chip load means your cutting edge of the tool is advancing 2 thousandths for every time it comes back around to the material. Axial depth of cut, that's axially. So that's basically in your Z. The depth of cut in your Z. Radial depth of cut is your depth of cut in the radially, so like your X or Y. Tool engagement angle, I think we'll pop up a chart for that here in a little bit, and I'm going to ask everybody on the call to hold me to that if I forget. But tool engagement angle is really what's happening with the optimal load in Fusion or HSM
It's
or
how
many
big
of
a
these
piece
other.
of the pie you want to take. It's how big a piece
It's basically
of the pie
how
you want
big
to cut.
the pie, right? Yeah. And it's the main driving function behind Mastercam's dynamic roughing, behind HSM and Fusion's adaptive roughing. I believe ModuleWorks is even calling it adaptive roughing. But what they're targeting is to maintain a constant tool engagement angle. And as Scott just said, it's basically the piece of the pie from the leading edge of how the tool's engaged with the cut versus the trailing edge of how the tool's engaged with the cut. And I am 99% sure I have this written down to talk about later. So we'll pull up the graph for that later. And then radial chip thinning, there's a graph for that too. But
just a thought here. I said, like when we're talking about all this stuff at the moment, we are talking about climb milling as well.
Yeah.
Rather than conventional milling. So yeah.
And I'm a donkey because that's a very important one that I didn't put in. So I had 14 parameters that we have to think about when we're adjusting cutting parameters. Now Scott just threw in a cut direction. You have climb cutting, which is like, I think about like a tire driving a car forward. It's climbing its way down the asphalt. Where if it was conventional, it would be like you being drugged forward in your car by a tow truck while you had it in reverse, right? That's essentially climb versus conventional.
I've always been confused about why they call it conventional because it doesn't seem very conventional to me.
May I?
Yeah, go for it.
Okay, so climb cutting is basically newer than conventional cutting. So for generations, when people had manual machines, conventional cutting was the standard. And the reason conventional cutting was the standard is because the machines were far more sloppy than they are today. So a conventional cutting condition, and go Google this. Well, I don't think we'll have a visual for this later, but you can Google the two if you're unfamiliar. But what it does is actually stabilizes the backlash in the machine. And you can have way backlash, you can ball screw backlash, you can backlash all over the place. And if you go to old sloppy Bridgeport and try to climb cut versus conventional cut, one is very, very chattery and one is less chattery.
Yeah, you can feel it on hand wheels, right, when you're advancing the machine. I'd completely forgotten, but I learned that at uni operating manual mills. So Thanks for reminding me. But yeah, you totally feel it. It feels horrible climb milling on a manual mill.
Yeah. And since we're going full geek mode, I think we're going to go geek mode long enough that Paul might have to drop, go help some customers.
It's okay. I'll watch the recording. Yeah.
So, hopefully we're not putting too many people asleep. But one other interesting kind of knowledge drop on climb versus conventional. We almost always climb mill especially with solid carbide tooling and in most CNC machining applications. There is an application for conventional milling with material that has like a scale, so like hot rolled type material. Material that might have previously been work hardened, right? Maybe flame cut material, something like that. Because then it kind of like scoops in the backside. But it generates a lot of heat because it basically starts the cut with a rub until it shears, creates a shear and forms a chip. And then the chip starts trying to carry out the heat after you've already created a crap ton of heat. With a conventional cut, the chip starts thick and gets thinner. With a conventional, it starts thin and gets thicker. So with climb milling, you start with a thick part of the chip, so the chip starts pulling out a ton of heat from the cut. So I'm actually glad you brought that up, Scott. Thanks for that.
Yeah, I often found that conventional milling with timbers and like plywoods could help because it effectively just pushes the grain back into the face of what you've just cut. So sometimes it helps kind of like smooth out, rub down.
Yeah.
Face, you know.
So another downside of conventional milling is that you're essentially throwing the chips out in front of your cut.
Yeah.
And then recutting them, which can be a problem. So chip evacuation is critically important there. So that is the basic fundamentals of cutting parameters, right? So we went from surface speed all the way down to radial chip thinning. Now, let me make sure I'm focused on. Now we're going to talk about. Let's see if I'm organizing this right. So those are cutting parameters. Now we're going to talk about tool geometry and the nomenclature of tool geometry, right? I don't know. If you're on this podcast, you're probably a super dork. So maybe this is interesting to you. If I was trying to give this chat with my daughter, she would have already left the room. So hopefully we haven't dropped too many people. But now talking about tools, so we're all on the same page is my intent with talking about all this stuff. Because all this stuff are the variables that add to our 16,000 different variations of things that affect our cutting conditions. So now talking about cutting tools and the details of cutting tools. So let's just go straight to flute count, right? You have a single flute in mill, like some of the Datrons are running single flute in mills. Two flutes, kind of when I started, two flutes were pretty common for cutting aluminum because they had a lot of, the term is in the rake area, I'm forgetting the term. There's a lot of room for the chips to get evacuated, right? But then you also, in relation to flute count, so you have your 2, 3, 4, 5, 6, 7, 8, 11 flute counts on some of these more modern tools. Now you also have flute pitch, and this is maybe less intuitive, but flute pitch is the orientation of the flutes around the tool center, right? So if the easiest example for me would be a 4-flute symmetrical tool, or with a symmetrical pitch would be you'd have a flute every 90 degrees. And symmetrical pitch is very common, maybe more common. Not today. Today is actually becoming more and more common that you'd have what they call a variable pitch. So using our 4-flute example, you might have one that's 38 degrees from one flute to the other, and the next one is 40. No, I'm already off. So one might be 88, degrees between them, and the next one might be 92. So they'd be staggered.
Yeah.
Now, Scott, what would be a good reason to stagger your flute pitch?
Well, to offset the, so you don't have depending on your, I suppose, radial depth of
Nothing like
cut or your
putting you on the
cutting
spot,
angle, you
right?
would change. Hey,
I said nothing like putting you on the spot. I know you
yeah,
know the
yeah.
answer,
It
so I
would
thought it'd be
change the
fun to
number of
go there.
flutes that are engaged or the position that they're engaged in the cut as they pass through in the material. Yeah.
Yeah, so that I think the main reason people think about a variable pitch,
It
flute
helps with
pitch,
harmonics.
is it helps with harmonics, right?
Mm.
So if you look at the harmonics leading up to that resonant frequency, it's very kind of sine wavy, right? It's very consistent, and that starts feeding itself, and everything goes to crap. What were you saying?
Yeah, so it's not just thinking about like how many. Again, it depends on the cutting conditions, but it's with higher flute count tools, depending on the depth of cut, you could end up with, like in looking at it in plan view down the axis of the tool, you could possibly end up with multiple contact points there, but also depth of cut because of the helix. You've got multiple contact points going up the tool as well, and so
Yeah,
the variable pitch will offset that too,
yeah.
as well as the next
You're
part.
getting ahead of my bullet points.
Yeah, yeah,
So points of engagement, which is great,
yeah.
points of engagement is a couple bullet points away. So let's pause that one for a second. That is a really deep, if anybody's got a notepad out, that's a really, not deep, but it's a very important topic, is points of engagement. So we'll talk about that in a second. A couple things to think about with flute pitch. Is a symmetrical pitch. We talked about this, probably very common. It's been the most common for generations. Variable pitch cuts down on chatter, and often a variable pitch tool can create better floor finishes. That's a little nugget for a lot of people. Some cutting tool companies do a good job of advertising it. Some don't. Some actually do a good job of purposely making it produce better floor finishes instead of accidentally producing better floor finishes. And the reason is about the best surface finish you'll get in machining is going to be with a fly cutter, a single tooth, face mill kind of thing with a fly cutter, right? Maybe a step up from there is going to be a face mill with a wiper insert. So you have one tool cutting and one tool kind of has a broader, more edged finished insert that comes back and wipes it, kind of polishes it.
Some end mills have wipers on the floor as well.
Yep, and that just stole my thunder. So yeah, no. So that's exactly my point. Some tool companies are smart enough to say, hey, we got this variable flute pitch tool. We're going to actually make wiper. The only downside there is variable pitch tools. One flute is doing more work than the others. So just keep that in mind. Where it's most important is with harder materials when you have tool wear. If you glance in there with an eye loop or put it under a microscope and you look at one flute might look fine. If you have a variable, you need to really spin it around, look at all the flute edges. You need to look at everything because there's one that's doing the brunt of the work. Now the benefits there almost always outweigh the negatives. So the next term would be helix angle, also incredibly important. Helix angle, I think, isn't talked about enough, and this goes to our next bullet point of points of engagement that we'll talk about more in a second. But the main thing to think about with helix angle is if we use one example, it'd be a 20-degree angle, which looks more vertically steep along the axis of the tool. That creates a significantly more side load on the tool. And there's formulas you can go, calculate all this reasonably easy. I'm sure there's calculators that are pre-made. Be careful with putting, these questions in like a chat GBT because a lot of these things will just invent their own formulas for some stuff. So if you do, put it in there and go just verify that they're using the right formulas and stuff. But a lower helix, so let's use a 20-degree as an example, is really good for pulling out chip evacuation. So if you're down in a pocket, they do a better job of shooting the chips up and out. And they're less ideal for finishing. So generally, I can make them finish good. I made, I keep bringing this up on the podcast, but I made my first 100% program toolpath part. I don't know, it's been a few weeks now. And I'm actually pretty disappointed with the surface finish on the walls and the floor, to be honest.
So was I, Tim.
Actually,
so was I.
Yeah, so was Scott, because he's an Insta machinist and we all hate each other, basically. But, and I think it looks good here, right? As long as I keep it moving and don't go full macro on it. But this is actually a really good example, because I have 2 half-inch tools out in my shop. One of them was in the machine, and that's the one I wanted to use. And that is a better rougher than it is a finisher. And it, I think, has a 30-degree helix angle. But it doesn't easily, and it does easily make very decent wall finishes and floor finishes. It's not a variable pitch helix, so it's a standard 3 flute, aluminum end mill. But it's kind of considered like a rougher finisher. Does a very fine job doing everything. To make good wall finishes, it needs a slower chip load, and I just ran it right through Toolpath, which has a pretty generic kind of chip load. Now talk about a high helix tool. We're talking aluminum, 45 degrees, something like that. That's going to have significantly less side load. So it's going to try to deflect less. It's going to try to bend the whole machine, in that kind of deflection kind of action. Quite a bit less. It's going to, but at a cost of having more pull-out force, right? It's going to try to pull itself out of the spindle more than the 20 degree. And that's calculatable. I'm not going to try to explain how to calculate them. It's all fairly easy if you have decent math skills and Google skills. But a higher helix angle is also going to more naturally create a better wall finish. It doesn't really have an effect on the floor finish. That's what we talked about on the flute count and flute pitch. That has more to do with the bottom of the tool, has more to do with the floor finish. So that's the basics of helix angle.
One of the things I learned the hard way there was how much axial force the helix and the number of flutes can have, and how willing it is to try and pull the tool out of the holder. So another whole but yeah.
Yeah, I have, okay, I do have a note when we're done with this. I'm going to share a story. I'll decide if I share the people's names or not, but I'll move on. But it talks about it, the story that I want to tie back to this is talking about all these little fine details might not seem very meaningful between a 30-degree helix and a 35-degree helix and a 45-degree helix, right? But all these things compound and add up for sure, especially when you're already maybe close to a limit of one tool. Throw in another tool, assume it's going to be the same. And it's not. So corner radius, that's the easy short one. It's the bull nose. I always forget the term that they would use for like a corner chamfer. Maybe that is the term. I don't use a ton of those. They seem to be popping up a decent amount in like Fraser tools, I think is that right, Ben? Fraser tools seem to have like a corner chamfer. Iscar.
Yeah, Fraser has the option for both. In fact, all of their tools, fun little fact, none of them are perfectly
sharp.
What would you call that? Sharp. I asked for some perfectly sharp ones, and they're like, "Yeah, we don't. They don't. We're not going to hold up."
Yeah, I should have. I planned on breezing past corner radius real quick, but it's worth mentioning. The tool cutting pressures are lower when you have a corner radius. Just the erosion and strength of that little tiny sharp point is pretty poor.
That's something I learned from Luke at Swift Carb as well, was that that's actually a point at really high wear or resistance on the tool, and so that geometry through can be critical for tool life, right? So
critical.
How many tools have you seen on the corners, right? It's because of that. So yeah.
Yeah, if you're cutting hard material, go Paul.
Yeah, so often they'll like I think they've figured out ways to get around it now, but instead of it being a tangential radius, it'll be truncated. And so
Oh yeah.
the most common place I see that play out is for like chamfer mills where they've got a slight tip radius and they're not true tangential, and then you end up getting different size chamfers. But they do it just to improve tool life.
What were you going to say, Paul?
I was going to say, last time we were on this call, we were picking on Lawrence for the bullnose tool ask and tool path, and actually today it seems like we've all come around. So
yeah, I love it. I mean, to be honest, I love. So to be specific about that, in Europe, I think it's more prevalent than it is in America. Drawings now are for harder materials, or maybe all materials. They're just having like notes that allow people to put a wall to floor fillets in all their parts. So I think that's wonderful. I'd love to see that trend, keep going more and more. I didn't talk about points of engagement. I just skipped past that one. But we were talking about helix angle and how a helix angle affects your points of engagement. So points of engagement is a very important topic, especially when it comes to cut consistency, chatter, all those things. So if you have a 20-degree helix at a specific radial depth of cut and chip load, you got to have a pretty aggressive chip load or radial depth of cut to have two of those flutes engaged at all times. And that's kind of the target. You typically want about two flutes engaged at all times. Anything more, you're burning up horsepower. Anything less, you create this frequency that really chatter loves to find, right? So if you have a 20-degree angle, you have to have a really aggressive chip load to have, or actually radial depth of cut's probably the bigger factor there, but to have the two flutes engaged. There's calculators for this. There's actually probably really good YouTube videos, I imagine, for this. Maybe we should do one at some point where a 45-degree, it's easier to get more, your two flutes engaged. But that's what most people are going to call points of engagement or flutes of engagement, something like that. So corner radius we talked about, cutting edge and edge preparation. That's literally just the edge that makes the cut. Edge preparation, honestly, isn't super common. I don't want to even say that. With aluminum tools, it's much less common. But edge preparation is taking the very fine, sharp edge and just giving it a little roundedness. Coatings will naturally do that. You get into some of the diamond coatings, it'll definitely do that. And then when you start cutting hard materials, they just need to, because with an edge prep, it adds to the what's the term I'm looking at? Survivability of that edge, right? It does create more cutting pressure. And then one little fun fact is, and you'll see them in tons of insert tools, right? Anything that has an insert tool, it's way more common that you'll see an edge prep, meaning not a very fine, sharp edge, but like almost a little fillet. It's worth knowing this applies to turning too, but inserts, anything that has an edge. If you have an edge prep, very often it's in the micron level, maybe as high as 1/1000th of an inch, something like that. A real fast way to find chatter is to have a chip load that's lower than your edge prep. That's a good little nugget. There's different ways to see it. Not a lot of companies. Some companies will give you that value, especially when you get into like titanium, high nickel metal, stuff like that, because their edge prep gets bigger and bigger to increase their survivability of their edge.
Well, I mean, also because inserts are pressed. Most inserts are pressed, right? So they're not ground. So that edge prep can only be achieved through what are effectively molds, right? Whereas with solid carbide end mills, they're ground, so you've got way more control over that edge prep.
Yeah. Yep. So that's a fun fact. Never feed lower than your edge prep dimension. Like almost guaranteed that it'll make a lot of very hard positions, stances. That's like that's asking for chatter. Rake angle is something a lot of people don't understand. So that is on the what I would call the leading edge. So anybody watching, I'm doing funny motions with my hands. The rake angle, if I was cutting this way, is the inside of the cutting edge, and that's the rake angle. So a positive rake angle, it lowers the cutting forces, better chip evacuation, and that's going to be positive. Would be, go look it up. I didn't make a visual for it. I'm giving you my hand gestures. Positive would be more like this. Neutral would be like this. It would be basically perpendicular to the cutting edge. And the negative would be even, the opposite of perpendicular. And so neutral is kind of a balanced general use. I feel like it's going to be better for like a harder materials, right? Most, I'm sure I'm wrong. Don't blame me for this. I think most tools are going to have a positive rake until you get into the really difficult to machine materials, and they'll have more of a negative rake. They're beating material off
it's
instead of
about having more support behind the cutting edge, right? So that you can, the cutting edge can support itself
in front of the cutting edge. More support in front of the cutting edge, right? So it's the rake angle is more about the front side, where our next topic. But to finish that, negative is a stronger edge, positive is a weaker edge. Negative takes more force to shear and start the shear of the cut. And positive generally creates less cutting forces to start shearing the material. Our friends over at AB Tool. Yeah, go.
Yeah, when I said back or behind the cutting edge, probably the wrong term, but just like it's just there's more material to support the cutting edge, right?
Support. Yeah, it's more material supporting like that underside in front of the cutting edge. The next topic is clearance angle or margin reliefs, right? That's the backside. That's the support from behind. I wanted to mention,
sorry to interrupt. Isn't that another difference between finishing tools and roughing tools as well? Is the rake angle?
Exactly. We'll talk about that. I got a story that I'll share, but I want to mention we're semi friends with the guys over at AB Tools, right? They're local to me. They've made for a long time a tool called the Shear Hog. If you look at their inserts, man, they have a very aggressive positive rake angle. And when we're talking about the cutting edge or cutting prep, man, they have no cutting prep, and it is polished, sharp.
But they grind rather than press their inserts.
Yeah, because they start with a pressed insert, and then they grind it to a really high polish with a real high rake angle. And what that does is it reduces the cutting forces. So on their website, they'll tell you how many. Trying to remember how they break it down. They basically say they give you a horsepower rating for inch. What a shear hog, the horsepower rating to remove a cubic inch of aluminum. And that not enough tool companies do that. We use some very generalized horsepower ratings for what it takes to remove aluminum or steel or whatnot. So I would love for more cutting tool companies to share their.
Have you played with a shear hog yet, Ben?
No, I've played with similar tools, but not an actual shear hog.
I'm bringing it.
They sound fun, that's for sure.
I'm bringing.
We need to get some at the shop.
You can play with one next week if you want.
I did a video. We did a tour at John Saunders came to town, and one of my life missions was to like watch a cutting tool, solid carbide tool being made. So here it is, the punchline. And I shared that. What's that?
Yeah, your screen broke up a bit.
Oh yeah, so here's the AB tool. They made that just for me because they knew I wanted to see a tool be made. But somewhere I shared, like I had a dream of watching a solid carbide tool. It's just like something I wanted to check off my list. So John Saunders was in town. We went and did a tour. He's got a really good video up about that. But then we went over to Selway. I had keys to the Selway office in the UMC that I was playing with. And we were doing some just sample cutting that I was using a shear hog on. And it was just murdering this aluminum at just crazy fast. Like, sounded great. I don't remember if John showed it or not, but chips, that was the old UMC before they put the lid on them.
Oh, yeah.
And so they used to just shoot chips up outside of the top because they weren't covered. And he got a bunch of hot chips down his shirt. So hopefully, if I remember right, he shared that in the video.
I've been wanting to bring this up through the call, and you've kind of probably a good point since you're talking about AB tools. One of the reasons why cutting tools, or certainly end mills, have got so much better in the last 10, 15 years, probably in the last 10 years, is because of a company called Anchor, who are an Australian company, which,
I didn't know.
I mean, I always got to be somewhat careful about giving shout outs to the Australians because, they deserve it in this case. Really, really cool company based in Melbourne and have super innovative. And they were kind of like the scrappy new kid on the block that came in the 80s and 90s and just continually innovate and have innovated through the last 20 years as well. Have made it so easy. And I'm probably overselling this, but certainly from my perspective, doesn't really know what they're talking about when it comes to grinding tools, but the maths and involved in trying to get the right grinding wheels and position them in the right way to be able to grind these end mills just blows my mind. But they figured out a way to be able to make variable pitch, variable helix end mills with wipers and all the rest of it, just banging them out, like so easy. And
this was cut on one, and it was very much like, hey, what helix angle do you want? How many flutes? It was like boop 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 boop, like ordering at McDonald's.
And
so with that done,
machines,
yeah. And AB in that video that Saunders did, it shows like the older way of making tools and the newer way, and they've just been, those machines over at AB Tools has been reproducing like bunny rabbits over there.
It just means they can iterate really fast as well, try out lots of different types of cutting geometries, edge preps, all sorts of stuff that just, game changer, really.
So we're getting close to wrapping up the understanding, of tool geometry and tool nomenclature and stuff. So we just talked about rake angle. That's very important to the strength of the cutting edge. Also important is the clearance or relief angle, margin relief. There's some of those terms, but what that is what comes after the cut, right? So you have the cutting edge and the material passes over that. You have a radial relief that after the cutting edge is kind of in a radial way. It kind of, falls away from the cutting edge. You'll see that more in a finishing cut, right? Because it's excellent clearance, because there's not a lot of physical cutting loads. The tool's less stable, and we'll talk about stability in a second, but you're basically not rubbing the material after you cut it, right? It forms the cut and gets off of it really nice. Typically allows you to have like a sharper edge. And then there's lots of different terms, but there's different ways that they create the relief after the cutting edge. And as Scott mentioned earlier, that very often is the difference between a finisher, a rougher / finisher, just a rougher only. And what you'll see is the more, often they give a relief by a chamfer, basically take from the cutting edge and just give it a chamfer, and there'll be a second one. So you'll have a primary and secondary relief, right? And a lot of that it does affect heat. It does affect the stability in the cut. So if it's basically supported behind the cutting edge by essentially rubbing the cut, it creates a more stable cut. So you can get away with more aggressive roughing. How does that translate to like, hey, I'm just in front of a machine. I'm trying to make a freaking decent cut. I'll share a story. So I was called late to a shop late one night from some people I respect a lot. Very, very smart people. One of them was like, man, I took this Harvey tool. Great. It was a helical tool, same company now, but I took this 5-flute helical, and I put in another 5-flute helical, and my cut just went to shit, just like that. I think they even sent me down the path of saying it was the same tool, or at least they definitely let me believe it was the same tool. So I had an hour in banging my head against the wall, and basically what happened is it went from like a beautiful cut, and I just trusted that they said it was, to a very chattery cut. And long story short, at the end of my ready to just admit I was a terrible machinist and maybe lost my mojo, I looked over at the two boxes and realized, oh, those are different freaking tools. And then I grabbed the tools and looked at them closely, and I don't think you can really see it very well, but on this tool, from the cutting edge, there's two reliefs, behind it. There's a primary relief and a secondary relief. And the difference on this tool, they were cutting steel. One of them was intended for finishing. One of them was intended for what they would call like a rougher finisher. Kind of do both, doesn't do either great. And then the other one was like hardcore, real proud rougher. It was just, the whole tool was designed for roughing. And the finisher was chattering like crazy. And I was mad and was like, well, let's find another one of these. And they're like, oh, I got one of those. And they put that in, the problem went away. And that was like the nuance of this trade, right? Is you can't take a 1/2 inch by 1 1/4 5-flute and put another 1/2 inch by 1 1/4 5-flute and get the exact same results. So that's the reason we're taking the time to give this, podcast, is to help you understand the different. I mean, it's not very exciting to go talk about, flute count and helix angle and points of engagement and corner radius and break angle and all this stuff. But it's important. It's incredibly important, because if I would have taken the time to look at and not trust these guys, right, I would have been like, oh, these are two different tools. Luckily, they had a rougher. They put it back in, problem went away. And they went back to using the rougher finisher just for finishing, and it was finishing great. You had a question, Paul, or do you got to drop? Oh, you're on mute.
Audio.
Oh my gosh, it sounds like you're saying something fun, or it looks like you're saying something fun.
Sorry about that. I do have to jump.
There we go.
I got to do call, but Tim, this is helpful for me. And, I think when we started off, like, what I was really interested in is, as somebody that's has less direct experience with this, it's really learning about these variables. And, I think I'm a listener more than a, presenter in this episode. And that's where I want to be with this. So I have a feeling this is one that I'm going to go back and listen to a couple times to try to make sense of this. And, especially as we think about like the future of setting up tooling, cutting parameter presets in Toolpath. This has been really interesting to hear you guys go on. So I'm going to drop. Thanks, guys.
Yeah. Go handle business. I'll depend on Ben and Scott to hold me honest, to kind of break down my summary of how I take all these inputs, these 16,000 options, and boil it down to like an actionable thing. So hopefully they'll keep going. Cheers. All right. Thanks, bud.
Yeah. Yeah. And to that point, this is making me think way more about it. And I've never really had to, I suppose, but just like the fundamental differences between insert tooling and solid carbide end mills from a cutting parameters standpoint, aside from the fact that often, you're going to, with insert cutters, you're more often going to be taking a wider width of cut, shallower depth of cut. And it's the inverse with the end mills, but you don't get the benefits that you can acquire through using a helical end mill, because you don't get those multiple points of contact up the shaft of the tool, up the axis of the tool. So
Can you take a note to let's dig into? We'll do a little free form. Dig into insert versus. Make a correlation between insert versus like long reach tools. When we get to that, if you can remind to bring that up, I think we might be able to make a correlation between the two.
Oh yeah, nice.
So the other thing when it comes to just tooling, geometry, nomenclature, stuff like that is coatings. We didn't really talk about coatings. I wanted to get to my story that I realized how clearance angles or margin reliefs kind of impacted this cutting story that I had. But coatings are another important part of cutting tools. So I'm not even going to try to list all the coatings, right? When I got in the industry, the only basically prevalent coating was like tin, titanium nitride or something like that, right? Now the listed coatings are super deep, super technical. A couple takeaways I would say here: coatings are typically for two reasons: to be like the Teflon on your frying pan or whatever, and be less sticky for like galling type materials like aluminum to stick to. So Harvey has a good one I never remember the name of, but it is actually really good at kind of repelling the galling of aluminum to it. Most coatings, I think, are used to add lubricity and create like a heat barrier for the substrate being the carbide, right? An important thing to know here is that many coatings, I would say most coatings, are ineffective, meaning have zero benefit, and maybe even a couple have a lower than zero benefit if you're not running them fast enough, if your speed isn't high enough to create the heat that they work their ideal conditions. So give you an example. Many coatings will say operating temperature 1100 degrees or 1000 degrees, something like that. What happens is you end up with a fairly narrow window of what's good for that tool because of the coating, and then also because of the substrate being the carbide. As a general rule, carbide starts to break down, degrade. I should have written this down. I have about 1,000, 1,100 degrees in my head. I think it's. Say it again.
I'm interested I'm sure Luke's told me all this stuff before, but it's I don't remember it, so it's interesting to hear you.
And the caveat to that is high quality carbide, right? Yeah. Swift Carb has really high quality carbide. Most of the cutting tools I use start with really good carbide, but it generally breaks down and starts to just life isn't good. 600C, maybe one of you can give me a fact check on this. 600C, 1,100 degrees Fahrenheit, something like that. Carbide starts degrading quickly, very quickly. And the problem is a lot of coatings like 900 to 1,100 is kind of their operating temperature, 1,000 to 1,100, 1,000 to 1,200. It all depends on the coating. So try to learn about the coatings that you're using. Don't get coated tools if you plan on just running them really conservative under that, because you're just paying for money that has no benefit to you.
On the topic of coatings as well, I think that's one of the areas now with, other than edge prep, coatings is one of the biggest differentiators between cutting tool companies now, because companies like Anchor have effectively democratized cutting geometry to the point that it's so easy to cut a geometry that's so easy to grind and manufacture that this is the next frontier. There's some pretty wild.
It's getting to a point. Sorry, cut you off. Go.
Yeah, some pretty wild science behind what they're doing with coatings to get tool life up there and improve surface finish. It's pretty,
And I'm starting to see more and more of these small companies offering coatings that were only offered by the big monster companies before. So
because the capital investment's high, but it's like one piece of machinery that you can install and learn how to use. You don't have to have an entire plant. That's why companies like Sandvik and Iscar and all the rest of it dominate the insert market, because the capital investment to be able to manufacture inserts is just like completely unattainable for mom and pop shops, right? So I like to refer to end mills, the market for end mills, more like craft beers, right? Whereas insert tooling manufacturers are more of a Budweiser rather than some nice little craft brew out of Portland.
Yeah, I love it. With that, we'll wrap up the cutting tool geometry nomenclature, that kind of general topic. There's a lot there, and I'm sorry if it felt like we're going super dork geeky on this, but I think we all have to be on the same page to start now learning about how do we deal with all that information, the 16,000 variables. Remember, if we had 14 variables, we had 14 variables on those lists before Scott threw in the 50th one. And if we only had two options, and we all know there's more than two coding options, right? If we only had two options for rake angle, which we have three that I listed there, we have over 16,000 variables. So how do you know kind of where to start?
Well, that's the thing, Tim. I know stuff, and I know more than a lot of people, and I possibly know more than some machinists about cutting tools. And I'm not a machinist, but I have always struggled and been intimidated by feeds and speeds. And I spent 11 years supporting CAM programmers around the world and writing post processors, but I always made it their responsibility to pick the feeds and speeds and to run those tools on their machine, because so that's why I'm excited about you dumping your knowledge. And even with feeds and speeds calculators, I never felt confident, because I didn't, to your point when you started this podcast, I don't understand it enough. I don't have that fundamental clarity in my mind about how to go about calculating feeds and speeds for any given situation. And so I'm excited about you sharing all this info and being able to learn from that. Great. So I'm sure others will too.
I hope so. I put a lot of thought into organizing it, right? So Carl Bass, one of my favorite people, mentors, the old CEO of Autodesk, I think was purposely trying to offend me one night when he said, it's just algorithms, Tim. Can't we, this all should be handled by computers. I remember I was he's smart. He knows what he's doing, right? I knew he was being provocative, but it pissed me off. And I probably reacted like that, and he probably thought it was hilarious. But then as I've matured and kind of my career's gone down a different path, it's well, it kind of is just algorithms. But there's a lot of stuff that algorithmically happen in our head that we haven't really written down and made a process to and made sense of. You have, in my opinion, that's why people intuitively can handle, cutting parameters. It's because they have these algorithms in their head. They might not even look at that end mill and mentally think oh, that was a big, a big clearance angle or margin relief. They just observe it and make these intuitive decisions. So let's get to my next main topic is establishing a good starting point. So I'm going to lean on the two of you to, I'm going to take us down a path, and I'm going to lean on the two of you to ask questions if the path doesn't seem to make a lot of sense, or if you've had other experiences. I like to think when I'm starting with a new cutting tool, I definitely wasn't given cutting parameters with this tool. I'm never going to cut with it. It's going to stay on my parts shelf as the first time I saw a tool getting made. But if I was going to start with that, what would I do? Well, I would start with kind of defining my goals, right? It's how I think of a lot of my life, to be honest. I'm going to go into a race. What are my goals? Was my goal to win? finish happy and healthy and have a good time. Those are two drastically different approaches to what you prepare for and how you handle the race, right? I think about the same thing, how much risk. If I'm going to win, I'll be willing to risk, right? So that's how I break down, I'm setting up some cutting parameters for this tool. What are my goals? Is it low cycle time? Potentially at sacrificing tool life and cost, right? Is it, a good balance of efficiency with tool longevity, or is my main priority? And to be honest, with the machine I have in my garage, this is my main priority, is prioritizing predictability and reliability. I see our industry has shifted a ton from cycle time to predictability, reliability. Process reliability was a term that was thrown on a ton, 5, 6, 7 years ago. And what's driven that? To me, it used to be, you would get a 3-axis mill, you'd put it in the shop, you'd hire a person, put in front of it, maybe hire a night shift to put in front of it again if you wanted to increase your productivity. But you had someone standing there watching it make parts, open, race to change parts, close the doors, hit cycle start. So your cycle time was super critical and important. And the easiest way to lower your cost was reduce your cycle time. Now we see more people multitasking, running pallets of parts, even in a 3-axis machine, right? They're running a pallet of parts, so they get, an hour of runtime on 2 different machines. One person can run 2 or 3 different machines. If they're running pallets, it takes them 5 minutes, 8 minutes to change parts, but the machine's running for an hour. The other thing we see is palletized machines, right? Multi-axis machines doing more in one, lower volume, higher mix jobs, and they're hopefully running them at night when it's kind of free to run. So that's, I think, one of the reasons we see process reliability, predictability, things like that being more of a priority. So moving forward from there, let's say I start my main priority is reliability and predictability. Those are kind of different things, right? So I start with the manufacturer's recommendations. I've got catalogs over on my bookshelf, and because there's so many variables that we went over, right? There could be 16,000 things we can, have to try to decide which is the best one. I personally think the best way is to start with the manufacturer's recommendations and I'm going to be specific, from a speeds and feeds table. Now that was a pretty particular point, because I particularly, and I try to be the happy, love everybody guy, but I haven't had good luck with cutting parameter calculators. And the problem is, I actually love some of the people involved in some of them. So I have conflicting, positions there. I've also worked with people that represented those companies on machines and found faults in them. I think Ben kind of highlighted one of the, you also had a similar experience. Is that right, Ben?
Yeah. I mean, not to put down any of those calculators, because when we were talking about that break off point, clearly I hit that with my 10 times tool diameter. I mean, I'll bet if I ran that same tool with a 3 or 5 times diameter, it would have been cake. It probably would have cut beautifully. Yeah. But it got to the spaghetti zone.
Yeah. So that's exactly my point. And my absolute single most main point is, you can science and data your way all the way, science and physics, or whatever you want to say, like all the way to some dreamland. But I haven't seen anybody do a good job at defining what I call a limit, some sort of limit. Pucker factor is a very valid limit. Just your own personal pucker factor. Horsepower is a limit. The resonant frequency is a limit. tool holder, grip force, a limit. We don't need to rehash everything we spent 2 hours. We have like an admission fee. You got to listen for 2 hours to get to the good stuff. So you paid your admission fee. We don't need to go back and rehash that. But that's my main problem with that. Why I struggle to. I've banged on them. I've spent hours of time with application engineers that are gnarly experience, and that's always the main issue, is that they don't help you define your limit point.
So why do you think feet and speeds tables from manufacturers are different in that sense?
Yeah, because they fall more in line with my personal experience, and I've worked with, I don't know, 9. I was trying to count last night. Let's say right around 10, like really highly qualified application engineers for cutting tool companies, from a range of cutting tool companies. And I've learned like they follow similar principles as me when they're making feeds and speeds tables, or speeds and feeds tables. Sorry, old man Frank. Is that they don't go and check every parameter for every one of those tools, but what they do is they have standardized testing that goes from their smallest tool in that catalog for that family of tools. They have one in the middle and one out towards the end. Here's the problem. They also have the same problem. So I might be cutting off your question. They also have the same problem because I find it all the time. Is with MA Ford is a perfect example. It's kind of the benchmark for many older people like me, is like the standard for good rougher finisher aluminum tools. That they'll send me right off the cliff, past my, in a very linear line. But for me, it's easy to be like, okay, I have a 1/4 inch tool. I'm going to start here. And I know from my experience with my machine and other machines that like right around here is the danger zone. So when I start getting up there, I'm going to go take the time to calculate, my horsepower draw. And I know like my machine's pretty happy with a nice short, tool system. My machine's pretty happy, right around 20, 23, 24, 25 horsepower. It's just happy as long as I'm in a shorter situation. If I have a long tool holder and a short tool, that's still not great, right? So for me, I invest in short tools, short holders, everything grip really good. And that's a place to start. And here's the reality. We all need somewhere to start, right? The other example that I'll use is if I had this tool, I don't have any cutting data on that tool. What I do know is it's 30-degree, helix angle. It's a 4 flute. Just looking at the margin relief and the rake angle, like it looks like a pretty typical, like, rougher finisher for like steel. I'm not here to pimp anybody's name. Like Harvey, I would go to Harvey and find a comparable tool with a 30-degree helix angle. They do a pretty good job in their tables of giving you usually a pretty conservative starting point. And at least now I have a starting point, right? From my starting point, I use some intuition, to be honest. I go through my library, see if I have any other tools that kind of fall in that same thing. I'm pretty adamant about finding a cutting tool line, a cutting tool company that I feel like I got good support from, that kind of thing. And like, I'm sticking with this line as much as I can. And then it's easy for me to like, oh man, I got the magic recipe on this one. And we'll talk about how I kind of adjust, parameters in a minute, but, and then I'll kind of extrapolate it from there, kind of getting a good feel, finding a limit accidentally, because I didn't take the due diligence to calculate stuff. We could calculate all kinds of stuff, but you have so many variables. Sometimes you just got to go get some work done and deal with what comes after it. Now, what sort of
I've always wondered, how conservative those feet and speeds and
Mm-hmm.
feeds tables are.
Mm-hmm.
And what sort of assumptions do you think that tooling manufacturers make?
That's a wonderful question. So thanks for that. Here's the other reason I try to stick with a general tool or general company. I referred to Harvey because they make such a wide range of tools. It's not hard to find a 30-degree helix 4 flute from Harvey, right? A company like Harvey, they give you very middle of the road parameters. Not super conservative, because I've run across lots of tool companies that give you like, what? I haven't seen numbers this low. I know you guys make good tools, but I haven't seen I haven't seen tables this conservative for a decade or 15 plus years. And then I take that tool and I'll start with theirs because it's a place to start. And then it's like, man, my let me look at my notes. One example is like cutting harder material, steels, titanium, stuff like that. One factor that you're looking for is heat, right? We talked about heat before.
Mm-hmm.
But one thing you're looking for in a low carbon steel is a good chip color, right? Stainless steel, good chip color. Titanium, good chip color. Doesn't mean it's the same as the low carbon steel, but you want some color in it without it looking ashy. Ashy is way overheated. And you'll know that real quick. Like if you're getting an ashy type, chip, it's a really dark color chip. Your temperature's super high, and you probably figured it out before you had time to deal with it. But using Harvey as an example, I'll take a tool. I don't have any cutting date on it, which happened way more than I wanted at Autodesk when I was running around doing demos, because it was like free tools, and I didn't have any cutting parameters. I had to start somewhere. And I'm like, all right, I'll start with, Harvey parameters because it's a place to start. I could find a like tool. And then the first thing I do is listen. If there's no chatter, I'm just going to run it. And I just, stop between cuts. And it's like, oh, I got bright silver chips on this, low carbon steel part. That means, what would you guess that means?
Well, it's bright silver. For me, that sounds like it's heading towards ashy. So,
so bright silver usually means you're under temperature.
Yeah, under
right?
temperature. Yeah.
Yeah. So then, if you look at a steel, you're going to get. Let's just put a ton of thought into this. Explaining this one, probably like a goldish color, turn blue, purpley color, turn dark purpley blue, turn to ashy, and then it's just black and ashy after that, right? Titanium would be. A lot of people don't like seeing color in titanium, but I'm telling you, light gold is good with titanium. Light goldy color is kind of transitions from titanium already has like a goldish color to it, but if it starts getting a little goldy, like you're finding that sweet spot with your temperature. So that's how I would react to it. Is aluminum. Very often you don't have enough RPM to over RPM aluminum. But when you do, you get galling, right? You basically create too much heat and you start getting welding or galling. Sometimes you have to see it under microscope. Sometimes you don't. Every time I say something like, basically don't have enough RPM to over RPM aluminum, Rob Lockwood will send me a spindle speed of some of his machines, right? So you can definitely over RPM aluminum. Easier on like a face mill, right? Easier to over RPM a face mill. Where
when you say over RPM, it's more about the surface speed, right?
Yeah, exactly. So very often, if your target surface speed is 2,000, 1,500, 1,000, something like that, you don't have enough spindle RPM to do that with an 1/8 end mill. With a 5-inch face mill, many of us have enough RPM to take it to an ideal surface speed in aluminum, and then past it. Now, past it is when you start literally melting the material, and you'll get just like micro galling or welding to the cutting edge. Now, when you want to flirt with that, you get into some coatings that have a what's the opposite of an affinity? You have like a
kind of a lubricity. Oh,
yeah. You have a lack of stickiness, right?
it's like Teflon for aluminium.
Yeah, like Teflon. There is a like an affinity is like a love for. There's like a repulsion, kind of term. Okay, so to try to get back on track, so yeah, you start with a point, you go cut. Chatter's the first thing I'm listening to. If I get chatter, what do you do? Make sure I'm following my thinking. Yeah, so if I get chatter, my first reaction almost always, if it's so bad it sounds like somebody's torturing a cat out in the shop, I stop it, I rethink, maybe go change my parameters in cam and come back. But if it's somewhere from pretty bad to kind of bad, I go to my overrides on my machine. I go spindle and RPM down, 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 down. So what that's doing is I go down 10% at a time for both feed and RPM. And what that's doing, it's maintaining a consistent chip load and it's bringing the speed down. If you can't get past, fairly quickly get past your chatter because of that, there's a good chance you just have a machine limit that just can't handle the parameters outside of your speed, right? If it's a speed, if the speed fixes it, you're like, okay, this is my window of speed, so RPM or surface speed, that I find this resonant frequency that wants to feed itself and make it worse and worse. So now you have a decision: do I stay under that? It's like there's a term, the excite, man, something excite, right? There's like, you're exciting the resonant frequency when you're in here. So now your decision is, do you stay below that or do you just go for it and get above it on my dirt bike scenario, right? Do I jump past it and get up above it? If you're way outside of your machine limits mean rigidity and stuff like that, yeah, you probably just found a resonant frequency. If you're flirting with what you think might be a limit, go down.
And most of the
Does that
time, you
make
probably
sense?
have to go down because you like. I'd say that a lot
Almost.
of people just can't even don't. They're not in the machine's not even going to be able to get to the point where it can move that fast, or it's
Yeah.
just not capable.
Almost always. I
Yeah,
almost always would go down. Yeah.
yeah.
And then the indicator to me is if I go down and I'm lower than 50% of what I expected to run it at, like stop, still chattering. That means I'm chattering from some mechanical limit. And it's almost never the cutting tool because carbide is freaking stiff. But you might get into a stack up of insert stuff. Insert holders are usually pretty rigid, but it might be a limit. Let's shelf inserts. Let's shelf inserts for now.
One of the on that point, I did a demo with a machine tool manufacturer in Australia a number of years ago for a trade show, and it was on a turret lathe, and we were trying to chase down this chatter issue. It was nightmare. We tried everything, absolutely everything. Just could not kill it. And then we noticed that one tool was very similar, was cutting like butter, and then this one was we just couldn't stop this resonance. And the only difference, other than some obvious things about the tool, the only difference between the two is one had a through coolant collet and the other one didn't. And so we went and got a through coolant collet and dropped it in, and the chatter went away. That was it. No matter how low we dropped the feeds into the speeds and feeds, it was still there, but we changed the collet out, and it just preferred I suppose just the resonance.
Was it a rubber sealed collet?
Harmonics completely changed in that setup because of that. Well, the slots in the collet, it wasn't NER collet, so the slots in the collet were different between the two, and it just completely changed the setup, and that solved the problem.
Turning is very often the variable in turning is something from the turret to the chuck.
So that was milling. That was milling on a lathe.
Got it. So that's between the turret and the chuck, right? So it's either your part. In your example, I would most collets have like a rubbery stuff between the slots of the collet, right? So I've taken rubber bands and put it around turned parts and had chatter go away because it absorbed that. It broke up the resonant frequency, right? So let's drill down on this starting point thing, right? So we had a place to start because we needed somewhere to start. The other reason the generic calculators that give you all the parameters, the reason I struggle there too is they very often they have sliders like the good ones, right? They have sliders for productivity. They have sliders for work holding and tool holder rigidity or whatever. And very often, as you move those, they only change the chip load. So that's another reason I struggle with those, because very often I find changing the cutting parameters, like let's say radial depth of cut, axial depth of cut, is more often it's the easier way to fix the problem when you get to a mechanical limit. Does that make sense, Ben?
Yeah, I was actually thinking about it. I think I've used HSM Advisor. I can't remember what it was, but like you can see in real time when the axial versus the axial versus the radial changes. You can kind of see how your feeds and speeds and things are associated with it. And that was really helpful for me. Regardless if I was using those parameters, you can see how everything is tied to it. And then as you adjust the rigidity or maybe the work holding setup, you can also see how those feeds and speeds are also going to be reduced, so you're not as aggressive.
Yeah, Scott, I know you stepped away for a second, so I'll just reiterate. I think one of the main reasons I struggle with some of the more like all-inclusive calculators that give you all the parameters is pretty often they have these sliders for like productivity, work holding rigidity, tool holder rigidity, some sliders like that. And then I believe, maybe somebody will correct me, but and I did fact check myself last night on 3 different ones. When you slide those around, the thing that changes is the chip load. Where I've had better experience, and I can make sense of it through calculating, deflection forces, pull out forces, things like that. Is it's just too simplified to just reduce your chip load.
Yeah, okay.
Because I've actually had just my anecdotal experience, and then also making sense of it through trying to do the math and understanding the math and seeing the patterns. My example earlier with that 5/8 tool is I've had better luck having good strong cuts by reducing my constant engagement, my step over, over cutting my chip load in half. I'd be better off cutting my often I've found I can cut my, step over down and then increase my chip load.
Well, that's why chip thinning. That's what chip thinning is, right?
That is what chip thinning is, right? So in our example before, that where I showed the chart, we showed just all we cared about was horsepower, and that's actually the flaw. We were having a debate, last week internally of should horsepower be the thing that helps us bend people's curve. And it's too simplified, because the question is like, what is the reason you're finding a limit? Is it literally horsepower? Or, and then we had a conversation of, do the machines just happen to have a rigidity that is also aligned with the horsepower? But if I'll try to share this example. Let me look at my notes and make sure.
I just need to just disappear for a second because my daughter's going to head off to school and I'm not going to see her for a week. So I'm just going to say bye.
No problem. I'm going to show Ben. I'm going to show another share of a spreadsheet, and this demonstrates let's just look at these first 3 rows, right? We have a 3/4 inch diameter tool that has a length below holder of 1 inch. And it's a flute length, so it's a stub tool, right? It's a flute length of 5/8. So the flute length is actually 80%, only 83% of the flute diameter. You follow me so far, Ben?
Yeah, I'm following. I gotta charge my laptop. It's about dead.
Oh, yeah, all good. So if we go through and we do a full depth of cut with this, in the axial depth of cut, and then we do a 35% radial depth of cut, that's a 26.5 horsepower cut. So if we took that same tool, but now we have a reduced shank kind of short flute long reach tool that's 6 inches, right? It's 6-inch length below holder. Same flute length, same axial depth of cut, and same width of cut. We come up with the same horsepower requirements, right? So if we look at these 2 examples, like on paper, they should both be fine, right? The problem is the second example is hanging out below the tool holder 6 inches, 8 times the diameter.
Yeah, it's a nightmare.
That's a nightmare. On a Cat 60 machine with a shrink fit or some Rego fixed type holder, Uberchuck, something that's just got a very strong, solid hold on it, that actually is totally fine. And I would have no concerns about that. But I can promise you, there's 2 approaches to deal with this cut from here. And let's just say we're using my VF2SS in the garage. One is our example before that we were showing. We could cut the chip load in half, and we would roughly half the horsepower requirement. But through my experience, I'll promise you that if I'm cutting it full depth of cut in the axial direction and just reduce the chip load, I will still have a mechanical limit from either the force on the drawbar and the taper spindle, all that stuff. It'll just still be a mess for me. So one of the things I've just anecdotally covered, and I haven't honestly been able to make math sense of it, is when you have some mechanical limits, spindle taper, drawbar force, overall system rigidity, rarely are you going to solve your problem with chip load. So typically what you would need to do is reduce your axial depth of cut. And often you can get away with increasing your radial depth of cut. So in this example, I have run this on my machine. So with the same tool as above, so it's sticking out of the holder, 8 times diameter, still a short flute. I have to go to like a 20% axial depth of cut. I kept the chip load the same, 2% of the tool diameter. So 15 thou chip load. But then I could increase the step over, the radial depth of cut. And I basically got about an 8 horsepower cut requirement for that. And that works really good on my machine. I don't have, and it pains me to say this, but I don't have a clear way to drive you to that other than understand your machine. Like if we used a Datron, is a wonderful machine, moves around like a ballerina. It's like the little sports car. They do really good with shallow axial depths of cuts, big radial depths of cuts, and just haul ass and cut all day. And it's because you don't have as much of your flutes engaged. Hey, Scott, did you see my example there? I know you had to step out and come back.
I just came back and
they,
saw this spreadsheet, but yeah.
Yeah, basically, it's if you just looked at the cutting conditions of these two tools, they make the same horsepower requirement. One of them just happened to be sticking out of the holder 6 times the diameter, or 8 times the diameter. Sorry, and so if all you're going is by horsepower, it's a false
Right.
it's a false hope, is what it is, right? So I've found when you're coming against rigidity problems, spindle pullout problems, you're better to engage fewer flutes in the axial direction because they create a ton of pull down force and bending force. We talked about points of contact. So then you can increase the radial, maybe you go to 15, 20%, axial depth of cut, and increase the radial depth of cut to hit those points of contact, right? You want to hit a couple flutes engaged all the time. And that creates a pretty stable cut. So that's the general direction I go when you start talking, over 5 times tool diameter, over 6 times tool diameter, especially when you get into short flute, relief shank, long reach tools. Other advice I have is I'm a big relationships person. I wouldn't be anywhere near where I'm at in my career if I didn't have a ton of good relationships. I made a habit of when my tool vendors would come visit whatever shops I was in, ask them if I could buy them a coffee, go chat with them, be as helpful as I could. A lot of the experience I have troubleshooting cutting parameters was because I had a good relationship with whatever brand, application engineer, and I would be willing to go to another shop and help them, work through someone's problem because I knew that would buy love for me. And then when I needed help, I had it there. So that's the starting point, right? So that's kind of where I start. Now, our next topic, I think we can wrap this up. It's a 3-hour or 2.5-ish. It's a long time to listen to all this stuff, but I think we can transition to kind of how I think about tool grouping. Next, we can get into, we already talked about the limits of generic, tool calculators. And then I'll kind of, wrap it up with kind of my practical adjustments, kind of how I handle that. So tool grouping, this is what we do with pre-tool at Toolpath. Pre-tool has a long way to go to be a real kind of final solution. Our original intent with pre-tool is to help people speed up their process of getting their tools inside of Toolpath so they can do estimates and stuff like that. I think we've achieved, a good portion of that. And then now from here is how do we help you get your tools in with your parameters, maybe help group your tools. Maybe how do we group your tools and then apply these kind of recipes or whatever across a series of tools, right? So I group tools. Most easy low-hanging fruit is my MA Ford 138 tool, 3x diameter. Those are a group of tools. And I would, with 100% confidence, apply a cutting parameter across the whole range until I had what I defined as some kind of limit. Maybe I have to go find that limit, but then once I find the limit and define it, I kind of adjust from there. Beyond that, if I'm grouping in a more broad way, three flute end mills of let's say 1 to 3 times diameter. I would group those together without losing any sleep. I would put some pretty generic parameters across that series of tools for cutting aluminum, brass, copper, all that kind of stuff. And that's one of the things we're working on with pre-tool. I mean, I think pre-tool is a very useful tool for just anybody using Fusion and not Toolpath. Because we do a really good job of adding preset namings. And then applying, some what the parameters in pre-tool are literally just parameters that I've come up with over the last 25 years. How I would group beyond that is, get into, it starts getting really scary when we start talking about short flute, reduced shank, long reach tools that are becoming more and more common. I think because a lot of tool companies are smart enough to make them, and aerospace type companies keep making parts that need them. I would group those in smaller groups, meaning 6 times diameter stick out. Often they're like 75% diameter, cutting flute, or 100% diameter cutting flute. I would be real particular about grouping those together, because when you're at like a 5 times diameter short flute long reach tool, very often you can engage 100% of that flute length because it's 1 times diameter. The difference between a 5 times diameter stick out tool and a 6 is huge. A 7, huger. An 8 is super duper huge. A 10, as Ben was expressing earlier, is like, I've never been able to, on a normal machine, I've never been able to engage a full flute length, even of any tool, of those short flute extended reach tools. I've always been like 15, 20, 30% axial depth of cut. And just be clear there, that's of the tool diameter. If I have a 1-inch tool, I'm going down 15% of that, 150 thou. That's pretty nightmarish if you have an 8 times diameter 1-inch tool, but many of us have had to do that, right? So then once you group them, put some parameters in them, and go do some testing. I'm pretty confident if you have a good narrow group of tools that if you find your 1/4 inch has a good parameter, now you relate that back to chip load to tool diameter, axial depth to tool diameter, radial depth to tool diameter. Those are the 3 that I chase. Once you kind of get that ratio, apply those across the whole set of tools. And then what you might end up chasing is one of those specific sizes at the surface speed that you're running will find this resonant frequency. So you just pull it down a little bit. That's kind of your special one. And then you might find that the machine limit, right? And I got a 20 times diameter tool. It's just, man, it just wants to bend my machine right in half, right? Mm-hmm. So I think our topics are getting shorter and quicker, and then we'll put it back on you guys to poke any holes in my in what I'm presenting. But common misconceptions is one of the things I wanted to talk about. One thing I hear, and Scott, I know you've heard it, is I've had really good luck with X brand, right? IMCO is a good one. IMCO, by the way, has exceptional cutting parameter tables. I think they do a very good job. We were talking about like who does that well. They do very well with that. And they're slightly more aggressive than what I would call like a middle line, right? Harvey, I love Harvey. I love Helical. They're way more aggressive. They want to brag about their numbers, right? I love Luke Swift at Swift Carb. I love his tools. My memory, I haven't used his tables in a while. My memory, he likes to have more aggressive numbers than I like to start with. Okay, we talked about group. So common misconceptions. The one I hear a lot is, man, I ran X brand tool, and man, those are garbage. I ran the same parameters that I run, same half inch diameter, 1 1/4 length of cut, same exact parameters, and it was garbage. Totally, absolute garbage. Hopefully, our first 2 hours of this conversation shows you how many parameters go into making that. Mm-hmm. If it's a reputable tool company versus reputable tool company, it's probably not a garbage tool. So if you're trying to compare exact parameters to exact parameters, like just think through it more, try to identify the differences, make adjustments from there. That's my main kind of tip for you, is try to understand why it's not better. And and I can almost always, with enough time, magnifying glass, whatever, be like, oh, okay, there's what's happening. Is this, the relief of this isn't stabilizing the cut. So this is probably better for like finishing, or maybe it's a rougher finisher instead of just a rougher. I do suggest people start off conservatively, observe how things are cutting, learn more about chip color, learn more about tool wear, right? Hopefully you guys are making enough parts and harder materials that you'll find like a consistent, if you have consistent parameters, you'll find like, oh, I get about 45 minutes in the cut in this, H900 17.4 stainless. I want to get that to 50 or 60 or 70 minutes. You start get a cheap microscope. Amazon has some good ones that you can plug into monitors and really think through the cutting edge. Google, cutting edge.
There's some great microscopes, like videos under a microscope of the cutting edge starting to deform the material, and then you just like,
oh yeah,
how this works at all in the first place is an absolute miracle.
It is mind bending, right? Yeah, especially when you look at the harder materials where they have a very much a tree, the cutting edge is
it's just blunt force trauma.
Right? It's just brute force, sheer. It's like it's how you can cut a car in half by running it into a telephone pole. It's just brute force, sheer, right? Yeah. So I actually was just helping someone through some cutting parameters the other day, and I was like, all right, go out there, have your hand over the speed and feeds, and just go down together. And he's like, holy crap! I never thought about like troubleshooting on the machine my crappy cutting condition. So let's put it back on you guys. We covered a ton. Do you feel like you have more in your tool belt to go deal with? Ben, you're out at the machine, and you started with something of sanity based on something, and you have chatter. It's not like hit the e-stop chatter, but you have chatter. Like, do you feel like you have like what would your first thing to do be?
Yeah, I mean, over the years, and like also just kind of doing this as a hobby, and breaking tools is like the name of the game when you just don't know what you're doing. But they're like 1/8-inch tools, so it's cheap. I think you kind of intuitively learn this without realizing it. Now, we were going into like rake angles and helixes and stuff like that, and that's getting into the weeds. We had the disclaimer of we're going to get geeky today. Which we did. But I think you start to get a feel for what your machine can do. Like, you really only know your machine as well as, or it better than anybody else, really, because you're familiar with how it runs, how it feels, certain areas where it likes to actually cut better. That probably is a performance issue that you should get looked at. But
you mean areas of the machine, like over in the upper right? Yeah.
I've
seen that. I haven't thought about that in a while.
Good over here. Yeah, but no, this has all been really good to just like remind myself the why behind it. And I think too, if you're really green at this, like it can feel super intimidating when you're like, I've got an end mill and I want to make a part. Or you feel really confident in aluminum, and then you get a job in steel and you're like, I don't know what to do. You deer in headlights kind of thing. And so going back to the basics and thinking of it, the past, 2.5 hours, and thinking through it from a pragmatic sense where everything is kind of tied to, chip load and tool diameter. And as long as you know what your SFM is, and I think this was a really good talk, and it just reiterated stuff for me and makes me feel more confident. But I can see this talk being eye-opening for a lot of people too, where it's like, oh, I had no idea that correspond to this. And I guess that's my couple cents on it.
Let me address something real quick there. So you talked about broken tools. If I'm being honest, I don't break a lot of tools. So I didn't talk about it. Broken tools. If we go back through what we were talking about, the broken tool is like a force thing. I mean, there's a lot of variables there, right? So broken tool could be a chip evacuation.
That was mine.
That was yours. No, okay.
It was a little homemade machine, and then I'm sitting with a WD-40 can, hating myself because I don't have
Yeah.
coolant. I
So
don't break anymore.
assuming, yeah, you know what we didn't talk about is ideal cutting conditions. That means proper coolant, good coolant flow. We didn't talk about air versus coolant. I mean, the punchline there, and this might be the most controversial soundbite worthy clickbait thing. I almost never, and when I say almost never, I basically mean never, do dry air cutting. I've done it. I've tested. I've never had. No, I've two times I've had better tool life than with good flooded coolant with a higher kind of
Because
concentration.
that's one of the interesting things about modern coatings as well. Is in some cases are like for steels, like don't use coolant because of thermal shock.
Yeah. So there is a very valid point to that, and with air blast, I haven't been able to very consistently be able to get good chip evacuation with the different air blast setups I've run on quite a few different machines. So what happens is almost the worst thing you could make is recutting your chips. So that's just a little provocative little throw in there. Somebody will hate me for that. Lawrence maybe will throw some hate on me. Let me talk about cutting for broken tools and cutting force, right? So the main factor for force is chip load, right? So assuming you're not packing chips and doing all that, if you're breaking tools, you likely have too high of a chip load for the cutting conditions. What were you going to say, Scott?
Yeah, I was just one of the moments in my life where I had to kind of swallow my pride. You know, I was fanboying over carbide end mills and Swift Carb and all the rest of it. Was just being at a gear machining shop, and it was a VF6, I think. They had a big round gear on the table, and just machine out a big bit of steel plate, and so there was just big pockets for lightning that they were machining out the middle. Now, solid carbide end mill doesn't stand a chance in that environment. Doesn't matter how much coolant or whatever you've got going on. The pockets are that big that when they get away from the cutter, they land on the other side of the pocket, and then by the time the tool gets over there, it's just recutting chips. And you just can't get away from the fact that you're recutting chips all the time. And so the most cost-effective way is to use insert tooling because you're going to trash tips, and so it's easier to stop the machine, replace the insert, and carry on again. So when it comes to cutting conditions, that's just some of the realities you've got to deal with. You just can't get away from them.
Yeah, much of what we talked about was assuming you had decent cutting or good or ideal cutting conditions, right? So where you would have less ideal cutting conditions, deep pockets. I just can't get my air blast on there, so I switched to coolant, things like that. So one thing we didn't talk about was insert tool versus solid carbide. It's a long conversation that I'll try to shorten up. So I typically treat insert tools similar to short flute, reduced shank, long reach tools. They typically take a shorter axial depth of cut and a bigger radial depth of cut. They have high feed type tools that angle the pressures of everything better. So learn about high feed tooling and how they change the pressure angles and forces. But there's still the point of engagement topic that's relevant there. The reason we take bigger step overs when we're in a shallow depth of cut is to engage more than one tooth, right? So if you have chatter with insert tools, look at that. Maybe you can add more inserts. Some people are like, oh, I don't have enough horsepower to run 8 inserts. Well, if you're really only using 2 of them at a time, you might actually have enough horsepower.
Mm-hmm.
Because the alternative is going from an 8 insert to a 4 insert is to stabilize the cut. To have 2 inserts engaged, you have to go really deep radially. It ends up doing about the same thing. So do what you want with that information. I'll call a shout out. I haven't gone to look, but PH Horn, it's a reputable tool company. I'm not endorsing them as a tool company. I run lots of their tools and drills and had success with them. They quite a few years ago, they had some really good content. That was at, maybe it was a West Tech or IMTS, workshop that I went to. It was hours long. If somebody can dig that up on the internet, it's probably a lot of good. They go over a lot of the formulas and all that stuff to make more of the physics make sense to people.
They've got some good videos on their YouTube channel. I've never watched any of them. I've learned a lot from watching Sandvik videos over the years. Not their marketing. Some of their marketing videos are a bit weird, but they've produced some really good educational content over the years that I've got a lot of value out of. But just looking at the PH Horn channel, just scrolling through the videos, there's some good stuff there. And when I searched earlier on about they've specifically got a video on solid carbide geometries, and they talk about some of the harmonics and vibration, and they've got flute count, pitch, and they've got good chapter breakdown, so you can just jump to different areas of the video. So it's good. It's worth it.
It's probably 12 years ago was like the workshop I went to. I honestly, I don't even remember where, but that was the first time I saw the points of contact or flute number of contact in relationship to helix angle, in relationship to radial depth of cut. And they basically roll it out flat, right? So they show you like flat how that impacts the cutting forces, and that it probably changed my perspective of that. That's why I called them out, because they're the first people I saw kind of put it in a flat diagram. With that, I'm done. I'll answer any questions you guys have. That's a deep one. I'm glad Paul brought it up. We'll see how many people can listen to the whole thing. I think we can do, as a company, I think we can do and will do a good job of making some follow-up content. I think it won't be cheap, because I think really there should be some illustrations involved. So I think it might be worth us spending, several months, not just, give me a day to prep for this, but maybe worth several months finding an artist. Right? So this is really just meant to be a starting point. Normalize some of these deeper technical thinking, terminology and thinking and stuff like that. With that, I'll shut up and answer any questions you guys have, if you have any.
No, I don't.
Yeah, I don't have any. A lot to think about, but
it's everything I've learned in 25 years summarized and articulated poorly probably is the reality. But well, you guys specifically know where I'm at. I'm easy to reach. Anybody else? I do my best to reply to people on Instagram if anybody has any questions, disagreements. More than I don't like disagreeing with people, but more than that, if some little magic nugget that you've picked up over the years, feel free to share that publicly. DM me, whatever, on Instagram. It's One Ear Tim. One Ear. My name's Tim. Reach out to us at the Toolpath Instagram account. I'll leave it at that.
Cool. Well, Tim, thanks for the Tim TED Talk. We're all inspired by it and have a lot to think about. So that wraps up this episode. And like, comment, subscribe. Tell Tim what you think of all of his speeds and feeds, or feeds and speeds stuff. And we'll see you in the next one, guys. See ya.
Take care, guys. Thank you. Bye.